Bismillahirrahmanirrahim. Assalamu alaikum dear students. I hope you people are fine. Our today class, that you can say our final lecture, is on machine health monitoring or condition monitoring. Our main focus will be on vibration analysis part only. In case of machine condition monitoring, we people have different available techniques that we people use within industry. For example, vibration analysis, thermography, oil analysis, acoustic emissions, for liquid detection as well. So there are a number of other analysis as well, kind of NDT analysis, magnetic particle inspections. So all of them are very useful in their respective domains, and it depends upon the application and area of interest. Because our whole course was about vibration analysis, so this module is basically created to make you people understand why we people have studied vibration analysis, different terms and techniques that are helpful for machine fault diagnosis. It will help you people to practically understand the application of mechanical vibration within industry. For example, how this field is helpful. Normally people deliver these lectures in first class. I have also delivered that lecture in first class, but it was only for a small time. But because now you people are strong enough, and now it is easy for you people to understand why we need to understand mechanical vibration. So course I am sharing with you people is basically a vibration analysis level 2 course. Yes. So this course is mainly focused on different fault diagnosis techniques using vibration analysis. You people will see how we can use data collected from machines using the proper instrumentation, kind of transducers or vibrometers. And so you will see how we can interpret that data in a proper graphical manner, and after the proper signal processing techniques, how we can identify different faults of machines. As mechanical vibrating structures, for example, in case of rotary machinery, you people know, for example, if you have an induction motor that is coupled with the power transmission system, 2 or 3 stage gearbox, and further it is connected to some pump or reciprocating compressor. So you people know there can be a number of faults within that system. For example, if we will talk about induction motor, then in case of motor itself, there can be a number of faults, and each fault will have a prominent frequency at which it will originate. For example, if you have an induction motor and inside it, for example, if its rotor is not properly balanced, or if there is some kind of looseness within winding, or if there is shortage within the winding of machine, or lot of other faults, there is eccentricity issue inside. So when we will have this issue, then obviously, as we have observed from the previous lectures, then that because of a prominent fault, there will be a frequency response function. Because forcing frequency, that is actually because of the fault, it will try to generate a fault frequency, and this frequency will appear in time waveform and power spectrum. And we people need to identify that frequency, where it is and how much it have amplitude. So within vibration analysis, we people will be using different terms like amplitude analysis, phase analysis. Okay, in case of amplitude analysis, you people will be going to measure the amplitude of the prominent vibration spectrum peak. That magnitude can be in terms of displacement, velocity or acceleration depending upon the frequency of fault. Okay, phase analysis have its prominent use. For example, it is used to distinguish between different prominent faults. You people will see in case of machine unbalance or misalignment faults, sometimes we need to measure the machine signal in horizontal or vertical direction that are collectively known as radial directions, and third direction that is axial. So all the faults, they appear in prominent direction. Maybe some faults will appear more prominent in vertical and horizontal direction, that both are called radial both are also known as radial directions. If you people will hear radial direction within slides, that means if we are talking about radial direction, then it means direction can be either horizontal or vertical. Okay, and if it is axial, that means direction is along the axis of shaft. So I have talked about prominent faults within the induction motor. So there may be the appearance of twice line frequency or eccentricity peaks within motor, because rotor is supported on the bearings. So there may be a problem on the inboard or outboard of the motor. For example, if there is some kind of problem within the bearing, so it also will have a prominent signal behavior. Okay, so for example, if we people have identified that there is a fault within the bearing, then our job does not end here. We also need to identify where is the fault actually originating. For example, within anti-friction ball bearing, is that fault found within inner race of bearing, outer race of bearing, or is it cage fault, or either there may be a grease problem, or if the rotating balls or spinning balls have kind of cracks. So these are faults will generate a particular signal behavior, and we need to understand the behavior of the signal in order to become a very good vibration analyst. In addition to induction motor, if I will come across a coupling, then there can be a numerous faults. For example, if induction motor and transmission system, power transmission system, for example 2 or 3 stage gearbox, if they are not properly coupled, they are, for example, if there is resistance of kind of misalignment within them, so what will happen? This misalignment can be of various types, either parallel misalignment or angular misalignment, or maybe mixture of both. So this fault will also generate a particular vibration signal. In addition, for example, if there is some kind of fault that is available in power transmission system like gearbox, if I will talk about gearbox, then again I need to first of all characterize either it is containing the gear trains or spur gears or helical gears or bevel gears. So method to analyze gears fault for all the cases will be same, but method of analysis, for example behavior of signal, we need to identify particular frequencies of the gears. For example, are they originating, and if they are originating, what is the amplitude, and is there any existence of the supporting frequency, for example sidebands. So if sidebands are also existing, then these sidebands correspond to which stage and which gear or pinion. So, this helps us to identify where fault is prominent. We can not only identify fault for the gearbox, but also we can identify where is the fault within the gearbox. Either it is in first, second pair or third pair or fourth pair. Even if gears have cracks or rubbed gears, or either there is existence of backlash, or there is the eccentricity of gears, or there if the gears are not properly aligned. So, all of these cases, or if the gear tooth is broken, so all of them will have a particular vibrational behavior, signal behavior, and we need to analyze the signal before going to a particular decision. So, in addition, if I will talk about different belt and pulleys fault, they also have a prominent vibrational amplitude, and reciprocating compressors, fans, they all also have a particular vibration behavior. Now, if I will talk about structural looseness or rotating part looseness, then again, if there is the existence of the looseness within the parts of machine, or either the whole structure is loose, then this kind of fault will also generate a particular vibration signal. Okay. In addition, not only vibration analysis is helpful, but sometimes we people also need to use some other available techniques like thermography, boroscopy, acoustic emission techniques, non-destructive techniques like magnetic particle inspection. So, these techniques are also very helpful to identify faults within short span of time. Now, it depends upon the application. For example, if we only want to identify a fault and want to replace the component, then this is one thing that you can say it is preventive or predictive maintenance. But if you are going to find the root cause of the fault, for example, why was that fault originated? For example, if there is a bearing failure, then you have identified that bearing is going to fail, you will replace it. But being a engineer, your job does not stop here. You should also identify why that fault was originated. For example, for uneven loading, or there was a misalignment, or maybe other problems as well. So, identifying that fault means you are going for the proactive maintenance. Nowadays, very useful toolkits and advanced instrumentation is available, by use of which you can measure vibration signals, vibration amplitude, and you can plot different signal representation like time waveform, frequency spectrums, orbital analysis, phase analysis. In addition, advanced processing techniques. You can apply different filters, low pass filters, band pass filters, high pass filters, or medium pass filters. These filters will help you people to make the vibration signal more clear, because you people know when you will collect vibration from the machine, then this signal will have a vibration from hundred of components of machines. Okay, so you can not identify easily that which component of machine have a fault originated with. So, in order to make your signal representation easier, we people use different signal processing techniques. In addition to time waveform or frequency spectrums, we people can also use empirical mode decomposition analysis (EMD) or wavelet analysis techniques, Hilbert transforms, that are very useful for transient vibration signals. As we people know, as I have discussed lot of machine faults, some of the machine faults are low frequency faults, some of them are medium frequency faults, and some of them are high frequency faults. For example, machine misalignment, looseness, static dynamic balancing problems. So, these all are kind of pulleys and belts faults. They all will appear in low frequency faults. In case of medium frequency faults, some kind of anti-friction bearings and pumps and compressor faults live here. And in case of high frequency faults, we people have a power transmission systems like gearboxes and anti-friction bearings that are used for the higher RPM. So they lie in the high frequency faults. So different faults have different stages of failure. For example, there are different stages of failure for the bearing. Normally we people discuss 4 stages of failure for the bearings. So we will discuss all of them in detail in our today lecture. So this is actually level 2 vibration course that is normally turned for the vibration analyst course, and these courses are normally offered by lot of vibration institutes, especially Mobis Institute, CVCM and other available resources. The references of the represented data go for Mobis Institute, Center of Vibration Analysis and Condition Monitoring, that is actually a nuclear power engineering reactor and technology. It is offered by the Pakistan CVCM, and they are offering number of the vibration analysis techniques, thermography techniques and acoustic emission techniques, NDT techniques for the machine fault diagnosis and machine health monitoring. Okay, so we are also very thankful to the Sumico technologies, because some of the data we people are using here belong to them. I am really thankful to all of them. So let's start with our today lecture. There are different courses that are offered by Mobis Institute, CVCM or Sumico technologies that are identified for level 1, 2, 3 and 4. Fourth category is the highest level, and normally people appear with level 2 course. So inshallah, after the discussed lecture, you people can easily solve paper for level 1 and level 2 techniques. These are very expensive courses. Normally industrial engineers are offered these courses, and they have to pay about 2 to 3 lakhs and the years of experience as well. And they require the years of experience, and after that they appear in the exam that is offered by the Mobis Institute for the Australian recognition. So what will happen, you people will be awarded with the certificate after passing the exam, and this certificate will be valid for few years. So amount of the certification varied from country to country. For example, within Pakistan you people can easily appear for level 1 under 1 lakh, and for level 2 you people have to pay at least 2.5 lakhs and about 2 years of industrial experience as well that are required. So let's start with our today lecture. Let me tell you people, your one absolute question will be from vibration analysis and condition monitoring today lecture. One absolute question for final exam will be from this topic. There will be total 5 questions within final exam. First question will be from vibration isolation or force transmissibility. Second question will be from design of vibration isolators. Third question will be from design of vibration absorbers. Fourth question will be from multiple degrees of freedom and Holz's method. Fifth question will be from inshallah condition monitoring. So here you can see there are different maintenance techniques. For example, breakdown maintenance, preventive maintenance, predictive maintenance and proactive maintenance. Basic difference between all of them is that in case of breakdown maintenance, there is a proper failure of the part, and you will see, for example, in case of belt drives, either belt will be properly damaged, and you can visually identify that fault as well. So what will happen, there will be a sudden shutdown of your machine, and you have to properly replace that part of the machine, and there will be a unknown time failure, for example maybe short term or long term. In case of preventive maintenance, you need to identify different parts of the plant. You need to develop a weekly schedule and maybe monthly schedule. Sometime maybe annually there will be 2 inspections for the preventive maintenance. So you observe different vibration signals of the machines and you can provide the report depending upon the condition of the machine elements. In case of predictive maintenance, you people can use advanced vibration analysis techniques and vibration analyzers to identify machine faults, and not only that, you can also refer to the prominent changes that you people want in order to make the asset health monitoring more reliable and accurate. In case of predictive maintenance, you people need to go for the root cause why the fault was originated. So maybe you people have to, it will take time and also money, but on the other hand you people will be going for the long term durable machine component, because you are going to identify the main root cause of the failure of the part. These two maintenance techniques are provided even in the case when the machine is working. For example, vibration of the machine can be collected when it is in working form, in working condition. But in above two states, you people have to turn off the machine and then only you can replace the bearing or the gears or the belts that are failed. But in case of predictive maintenance, you people will have enough time that will be scheduled. For example, you people know that this part of the machine have a bearing and it is going to fail within the coming 2 months. So you can provide a suggestion within the report that please shut down the machine within 2 months. If it is coming under the schedule, then please replace the component. Okay, and in case of predictive maintenance, you can improve the reliability of the machine. So this is your breakdown maintenance. It implies the repairs that are made for the equipment when it fails and it can not perform its normal function anymore. Okay, it has the concept fix it when it fails or when it breaks. Very important. In case of preventive maintenance, it is also known as shutdown maintenance. This is based upon the time intervals. For example, a better technique mostly used by processes industries, life of every part or machine is calculated, very useful, and is very useful for seals and oil and grease programs as well. So these are preferred for the predictive maintenance. Preventive maintenance. What are the drawbacks? Most of the parts do not attain their maximum service life. Inventory of all the items has to be maintained. This is your predictive maintenance. It is also known as condition based maintenance or online condition monitoring. This approach uses non intrusive technologies to determine the actual condition of machine and its rate of failure. Different techniques are adopted, which include vibration checking, oil analysis, noise analysis, thermography, ultrasonics, and temperature, etc. Modern technique of the maintenance, that is predictive maintenance, mainly introduced in last decade of first century. The life of the equipment is monitored continuously and remaining life is estimated. This can be very effective in extending machine life with big financial savings if the implemented properly. Benefits of the predictive maintenance: no need of maintaining the inventory, shutdowns are planned to confirm good condition of machines. It can detect developing problems to determine the nature and severity of the problems and to schedule repairs that can best fit with the production and maintenance needs. So this is the very important technique known as predictive maintenance. It often referred to as root cause analysis. Okay, this philosophy works hand in hand with the predictive maintenance, eliminating the source of the fault to try to prevent it from reoccurring. What are the benefits? It do not require the stoppage of machine. Very important. It results in maximum output with the minimum inventory and unplanned shutdowns. So what is today industry demand? It is the desire is more performance for less money. What are available maintenance techniques? Predictive maintenance, proactive maintenance, that are very important where machine is in running condition, while in preventive maintenance or breakdown maintenance, these are normally, this is preferred over the breakdown maintenance, but it is visual technique where the only replacement is upon the visual inspection of fault. So these two techniques are very important and intelligent because you have to identify the earlier failure. For example, you have to predict either component is going to fail towards the failure. Okay, and if component is going towards the failure, you have to properly recommend the precautions, and you can eliminate fault within proactive maintenance. So what is vibration? All machines vibrate. The vibration changes as the condition changes. If you do not understand the basics, you will not be successful in vibration analysis. What is simple harmonic motion? You people already know the motion of mass and spring. Different spring cause the mass to vibrate at different frequencies. The free movement of shaft in the journal bearing will cause it to vibrate with the forcing function that is applied. So you people can say, what is amplitude? So if this is the time waveform signal, you people can see that then the distance between maximum amplitude and minimum amplitude is your amplitude. It is relevant to the vibration severity. Amplitude provides an indication of the amount of movement, the velocity of the movement, or the acceleration of the movement. There are some important terms used for amplitude analysis. For example, root mean square value, average value, peak value, and peak to peak value. These values have been collected and trained for many years. So here you can see within graph, this is your mean line and this is your peak. Then distance from mean line to maximum amplitude is your peak value, and distance from peak to peak is your maximum amplitude. And you can say, if you will multiply it with 2, if the graph is a proper in sinusoidal motion, then twice of the peak is peak to peak value. So how you can find the RMS value? You can find RMS value by dividing peak amplitude with square root of 2. That is actually derived from the above formula. In other words, you can say, if you have a vibrometer, you can easily measure the vibration of the machine in RMS peak value, peak to peak value, or 0 to peak value. It depends upon the application. Normally RMS value is preferable over others. Okay, so basically what happened within the analyzer, they just have to, they have a programmed environment where peak value is automatically multiplied with 0.707 and RMS value is displayed on the screen. So the waveform is also known as strong waveform, and it is the electrical signal from the sensor. For example, if this is your machine element that is rotating, and this is the outer covering, and this is your connected transducer, this is collecting vibration data of the machine, and this is your electrical signal representation in the form of time waveform. It shows how the vibration changes with time. So if there are 5 cycles appearing within 1 second, then you can say frequency of machine is 5 cycles per second or 5 hertz. What is period? It is the inverse of frequency. Introducing period. Period is the reciprocation of the frequency and it is measured in seconds or milliseconds. For example, for the below signal, you can see from this end to this end there is a one complete cycle, okay, and you can measure the time for this instant, that will be about 0.35, and here the time will be 0.15. What you will do, you will subtract 0.15 from 0.35, and at the end what you have to do, this will be your time period, and if you will take its inverse, it will be your frequency, okay. Vibration units. Vibration is normally measured in terms of displacement, velocity and acceleration depending upon the nature of fault. Low frequency faults are preferable to identify with displacement. Velocity is preferred for medium frequency faults, and high frequency faults are more identified using acceleration. So they describe 3 different characteristics on vibration. So we can see vibration data in all of them. Displacement. What is displacement? How far up and down the spring moves, okay. Unit can be peak to micron, mils peak to peak, or micron peak to peak. So what is 1 micron? 1 micron is nothing but 1 micron meter, okay, or 1000 of the millimeter. And what is 1 mils? It is actually 1000 of the inch. So it is commonly used when you are interested in low frequency fault. I am talking about displacement. It is commonly used when performing balancing, okay. What is velocity? Velocity is the rate of change of displacement and most important vibration unit, that is measured in millimeter per second or inch per second or RMS value. So it is generally good to measure most of the speeds and frequencies of interest. Units of velocity are used when the frequency of interest lies between 2 hertz to 2000 hertz. So this is the application of velocity unit. Whenever your frequency fault lies between, or frequency of interest lies between 2 hertz to 2000 hertz, then you should measure the vibration amplitude with velocity unit. So what is velocity? Velocity is the measure of the severity of the fault. What is acceleration? Acceleration is the rate of change of velocity. It can also be described in terms of G's value or millimeter per second square or inch per second square. So what is actually acceleration? It is actually the proportion to the forces within the machine. So it is very preferable for the high frequency faults, and it is preferable for the machines that are operating above 10,000 RPM. So high frequency fault analysis, high frequency faults normally include bearing or gears fault. So whenever RPM are greater than 10,000, then acceleration is preferable over displacement and velocity. So if you will compare all of them, displacement is more sensitive for the low frequency fault. Velocity is sensitive across the entire spectrum. It is not very ideal for low frequency fault and not very ideal for high frequency fault, while acceleration is very sensitive to high frequency faults. So these are different ISO standards that are provided across years and years for different types of machines, and for it also consists of different parts. For example, here you can see ISO 10816 standard, and it consists of about 5 parts in which general guidelines are mentioned. Also it is mentioned in second part, for example, large land based steam turbine generator sets in excess of 50 megawatt industrial machines, gas turbines, machine sets of hydraulic power generations. So it is applicable with different parts. For example, here you can see this is your ISO 10816 part 1, and it is applicable for general machines. Here you can see you have class 1 category machines that are actually small machines, category 2 machines that are medium machines, category 3 machines that are large rigid foundations, and category 4 large soft foundation. Here vertical you have a velocity in inch per second, here velocity is in millimeter per second, and green is the safe region or good region, and light green is satisfactory, and light red is unsatisfactory, and red is unacceptable region. So you can measure with category. For example, you can see category 4 is safe up to 2.80 millimeter per second. If it is operating, it is in under good condition, and if its amplitude is 7.10 millimeter per second, its condition is satisfactory. Okay, and if its amplitude is 18 millimeter per second, then its condition is unsatisfactory, and above 45 it is highly unacceptable. So these are the ISO 10816 guidelines. You can see them for general machines. This is your 10816 industrial machine guideline. This is your guideline for the industrial fans, ISO 14694. This is your design guideline for the balancing grades. Okay, not only this, let me show you people different grades or vibration standards that are available for different kind of machines. For example, this is your ISO 10816 and first standard that is actually offered for the evaluation of the machine vibration by measurement on the non-rotating parts. So this is your part 1 that includes general guidelines, and this is complete booklet. I will upload it on the website, and you can go with this guideline. For example, how to measure the vibration amplitudes, where to measure vibration amplitudes, and how to identify faults for these kind of machine elements. This is the vibration severity chart with x-axis as frequency and y-axis velocity millimeter per second. These are different categories of machines, and these are the corresponding boundary zones or limits. Okay, and this booklet is online available as well. You can study it. This is your ISO 10816 international standard guideline, that is for part 3, industrial machines with nominal power above 15 kilowatt and nominal speed between 120 rpm and 15,000 rpm. Again, this guideline is built up for that particular general category. This is your another ISO 10864 guideline for evaluation of the machine vibration by measurements on the non-rotating parts, that is for the gas turbine driven sets excluding aircraft derivatives. So this is its application, bibliography, where its scope, normative references, measurement procedures are discussed, how to evaluate the vibration amplitude, vibration magnitude, operational limits. So, and where are the vibration alarms and tripping boundaries. This is your another 10865 category standard that is provided for machine sets in hydraulic power generating and pumping plants, and again its scope and application is provided. This is your another ISO standard 10816 type that is provided for reciprocating machines with power rating above 100 kilowatt. This is your another vibration standard 13372 that is for condition monitoring and diagnostic of machines vocabulary, and here you can see its application as well. This is your another international standard 13373 part 2, that is for the processing, analysis and representation of vibration data. So how to represent vibration data, available techniques, how to apply the filters, what is enveloping phenomena, how to find the frequency response functions, how to find out the spectrum. So all of these standards are available for each category of faults. This is your another ISO standard that is also available. This is for balancing flexible rotors, with ISO 1134221998, that is actually for the mechanical vibration methods and criteria for the mechanical balancing of flexible rotors. So its criteria, application, procedure of balancing, 2-plane balancing, 3-plane balancing, all things will, and the available charts will be discussed in detail. And this is your ISO standard for the non-rotating parts, that is actually your 10816 ISO standard. For example, it is for the part to land-based steam turbine and generators in excess of 50 megawatt. So in addition, number of other ISO standards are also available. I have just shown you people some examples that are very helpful for you people in the future when you people will be working in some industry. So first of all, you people need to identify or characterize the machine, for example in which category it lies, and then you have to identify ISO standard, and then after the vibration measurement, for example some people are very confused how to measure the vibration. Then for each general category of machine there is a proper ISO standard in which there is a complete guideline how to measure the vibration, how to perform data analysis, how to identify faults. So you people just need to go through these ISO standards that are implemented at international levels. This is your introduction to phase. What is phase? Phase relates to the timing of two signals. Phase is very useful when diagnosing faults. Phase helps us to understand the relative motion of different points on the structure, and it can be measured with single channel analyzer or two channel analyzer and strobes as well. For example, here you can see this is your 0 degree location, 90 degree, 180, 270, 360 degree, again 0 degree, 90 degree. So this is the one complete rotation. For example, from this peak to this peak there is a 360 degree complete rotation of phase. And when you will apply transducer on the bearing support, then you can generate or measure the phase, where direction of the measurement of the signal is very important. For example, if you are measuring signal in horizontal direction or vertical direction, both of directions collectively are known as radial directions, or either if you are going to measure the vibration in axial direction. So here you can see the both measured signals are going with same behavior of signal. So this time waveform is basically going in phase. Here you can see this blade is moving up and this is moving down. What does this mean? That his time waveform will be like that and his time waveform will be like that, and you can easily see that its time waveform is out of phase. So measuring phase, we measure phase for two reasons: when performing balancing and when trying to relative movement of different points of a machine. For example, if you want to identify motion vectors of machine, for example how different parts of machines are moving either in phase or out phase, how much degree they are going in phase or out phase. So we can use term absolute or relative phase as well, that are actually the references for the measurement of the phase, either a fixed value that is known as absolute value, or the phase difference between 2 points, that is relative phase. So this is how the vibration spectrum is created. You people know that machine consists of number of parts and each part will be rotating with particular rotational frequency. So maybe this green part is coming from some set of gears, maybe this red part is coming from motor RPM, and maybe this part is coming from belt and pulleys. Then what will happen? They all are appearing in with particular vibration amplitude and particular frequency as well. For example, you can see within this time limit, this is your high frequency fault or high frequency signal, this is your medium frequency signal that consists of medium level of cycles, and here you can see minimum number of cycles are here. So this is your low frequency fault, and here number of cycles were very high, so this is your high frequency fault. And when you will see combined time waveform, it will be appearing like that. On x-axis it will be time, on y-axis it will be amplitude, and combined signal will be very complex. When you will add all of them, you will get such a complex behavior of amplitude, going up, down, up, down, up, down. There will be no specific behavior, okay? And this is the individual behavior in amplitude and time domain. And when you will take its frequency analysis and develop its spectrum, then what will happen? This is side view of the spectrum analysis. On x-axis there will be frequency, on y-axis there will be amplitude, and these are your frequency peaks. For example, this is your low frequency peak, this is your medium frequency peak, this is your high frequency peak. Amplitude identifies how severe is the fault. Phase identifies where is your phase identifies when is your fault occurring, and frequency identifies where is your fault originating. So this is your fast Fourier transform. Fourier provided that any real word complex waveform can be separated into simple sinusoidal waveforms. Okay, as the sine waves are separated from the combined waveform, they are converted into the vertical peaks which have a amplitude and position. Frequency domain representation of a time waveform signal is called vibration spectrum or fast Fourier transform spectrum. Okay, so what is frequency domain representation? Frequency domain representation is actually the frequency representation of the time domain data. So that is known as fast Fourier transform spectrum. So here you can see this is your 1x peak, that is your frequency peak coming from one of the component, this is coming from some other component, this is coming from some other component. So this is your orbit. What is meant by orbital analysis, or what are orbits? If we look at the time waveform from a sensor displacement, we will see the familiar pattern. Okay, if we move the sensor to another position, the pattern is same, but in this example we are at 90-degree phase difference. Initially we were here, for example we were measuring here initially, this was your time waveform. Now we are measuring here, now this is your time waveform. Okay, so what does this mean? Initially you were at horizontal position, this is your vertical position as well. Okay, so this phenomena of two time waveforms against each other, we call it as, we will draw a cycle. When you will combine both of them, you will get a circle. So this is basically, it shows how the shaft is moving. For example, normally the orbit analysis is performed for the shaft. For example, either shaft is moving, how is the behavior of the shaft within anti-friction bearing or journal bearing, it is moving in phase or out of phase, how much is the vibration amplitude. So orbit analysis help us to identify the behavior of shaft. It shows how the shaft is moving inside the bearing. This is also called as Lissajous figure or an orbit. If the shaft moves out and more in vertical direction, for example up down, then what will happen? The up transducer will be getting higher amplitude and horizontal sensor will be getting lower amplitude. Cycles will be same, and when you will combine both of them, you will get a circle. Because horizontal amplitude is small, you can see horizontal coverage amplitude is small and vertical amplitude coverage is large. That means machine is moving in more in vertical direction. Machine shaft is moving more in vertical direction. Okay. Here you can see the behavior of the orbit. It is not pure vertical and not pure horizontal, but mixture of both. So orbits are used to analyze the movement of shaft in journal bearings. 1s vibration is often used. What is meant by 1s vibration? For example, if your machine is moving with 2400 rpm, okay, then what will be its frequency? 2400 divided by 60 and it will be 40. So its frequency will be 40 hertz. Okay, and I will name it turning frequency. If induction motor rpm were 2400, then its turning frequency is 40 hertz. Okay, and what does 1x means? 1x means that you are at 40 hertz, 2x means you are at 80 hertz. So that means twice of the turning frequency. Okay, if 3x, you will get 120 hertz. That means thrice of the turning frequency. Okay, and if 160 hertz, that means 4x, that means 4 times of turning frequency. So these are also known as harmonics. 1x means first harmonic, 2x means second harmonic, 3x means third harmonic. So in this lecture, we will be going for imbalance, eccentricity and bend shafts, how time waveform and frequency spectrum signal will be looking like. We will be going for misalignment, cocked bearing and short foot problem as well. We will also be going for mechanical looseness, analysis of gears. Gears itself consists of number of faults. Mechanical looseness, it may be from the structure, whole structure, or it may be from the sum of the component of the structure. In case of gears fault, there may be there may be a eccentricity fault, backlash fault, there may be a development of cracks on the teeth, or maybe the breakage of the teeth. Okay. In case of belt driven machines, you will see there may be rubbing within the belts, or maybe belts are loose or development of cracks within the belt. In case of rolling element bearing faults, you will be going for the either inner race fault, outer race fault, ball pass frequency fault, inner cage frequency fault and train frequency fault. So you will see all of the faults have a particular frequency at which they originate. Analysis of induction motors as well, I have explained it in detail before. Analysis of pumps, compressors and fans as well, and we will also go for resonance and natural frequencies. Why resonance and natural frequencies? As you people know, if vibration is a fire, then resonance is its fuel. Okay, what does this mean? It means that if structure is vibrating, then if it is vibrating more, then the main power source is actually that structure is resonating. So if you want to control the vibration of the machine, you need to control the fuel that is actually making the machine amplitude more and more. Imbalance, eccentricity and bend shaft. Please adjust volume of your headphones if you people are using. Now let's see. You people have heard that some of the vibration analysts, if they are working from years, and even some old people can identify machine faults from sound as well. So it basically depends upon the frequency of vibration and the amplitude. So as different fault frequencies originate with particular amplitude and frequency, so what will happen, we have to identify the sound, for example, to which frequency it belongs, and after that we can easily identify from which part of the machine it will be coming. For example, here you can see in the frequency range of sound from 20 to 20 kilohertz, and please listen to it. As frequency is increasing, sound is going to a peak value. So let's go for the mass unbalance. A short geometric center line and mass center line do not coincide. So what does this mean? For example, if this is your shaft center line, and there will also be a center of the mass, and if we will draw the axis for both, if they both are lying on each other, that means that your body is properly balanced. And if they are away from each other, then now it depends upon the pattern how they are away from each other. For example, if both axes of the either geometric axis and mass axis, if they both are parallel to each other, then it will be of one kind, and if they are not parallel to each other, then they may be possibility then they will coincide with each other at a point. So earlier case was about static balancing, and later case is about dynamic balancing. The center of geometry is the line through the shaft and the bearings. The center of mass is the point about which the mass is evenly distributed. Causes of imbalance: because uneven dirt accumulation on the fan rotors, lack of homogeneity in the materials, cracked rotors, uneven corrosion, uneven mass distribution in electrical windings as well. So how the spectra will be looking like? We can expect to see a high 1x peak in the radial direction. I have told you people that radial direction basically consists of horizontal and vertical direction, and you can measure vibration in any of the direction. Normally the direction of the shaft is, for example, if you are going to place your sensor in such a way that axis of the sensor is parallel to the axis of shaft, then this will be your axial position. Okay, and if axis of the transducer is perpendicular to the axis of shaft, it will be your radial direction. Now this radial direction can be of different types. If it is horizontally perpendicular, it will be horizontal direction, and if it is in vertical direction, I will show you people in later stages how it looks like. So when you will measure vibration data, you will see a prominent 1x vibration peak. What does 1x mean? That first harmonic peak will be more prominent. Sinus time waveform will be looking like that, and phase analysis is very important for this kind of fault. So there are normally three types of unbalance: static unbalance, couple unbalance, and dynamic unbalance. Static unbalance is the condition where the mass center line is displaced from the parallel to the shaft center line. So there will be parallel misalignment. For example, this is your case study. In this case study, you can see that the spectra plots show a dominant 1x peak. For example, this is the dominant 1x peak that actually originates, and it is measured in, for example, this is F1V, this is F1H, V for vertical, H for horizontal. That means this is the value for first direction of the machine. That may be one end of the machine. So vibration is measured on the bearing. This is your first bearing data in horizontal and vertical direction. This is your second bearing data in horizontal and vertical direction. And you can see the amplitude should be amplitude should be checked in both radial directions to confirm this problem. The fan was recommended to be cleaned at the next available opportunity. Why? Because this fault is basically about unbalance. Now this is your eccentricity. Shaft center line is not coincided with the rotational center line. So how it will be looking? Eccentricity generates a very similar vibration pattern to the unbalance. The object pulley or gear will wobble around the fault center, producing a strong radial vibration because it will have a particular forcing function or forcing frequency. And what will be its value? F naught is equal to me omega square. Omega is the forcing frequency, m is the unbalanced mass, e is the eccentricity distance. For example, here you can see here this is your e, this is the mass of the unbalance. So F naught is equal to me omega square is your forcing frequency in this case. In case of eccentricity, a strong periodic vibration is produced because of unbalanced force along the length of the belts. So what will happen? We expect to see a high 1x peak in the radial direction. Again, for example, if this was your bearing, okay, and if you are going to measure vibration in this direction, this is your horizontal, this is your vertical direction basically, okay, perpendicular to the axis of shaft. If you will measure in this direction, this will also be perpendicular to the axis of shaft, but this will be your horizontal direction, okay. And if you measure along the axis of shaft, then what will be? It will be axial direction. For example, if I'm going to measure vibration perpendicular in this way, I am placing sensor here, this is my sensor, this will be your vertical data measurement, this will be your horizontal data measurement, okay. And if I want to measure axially, I have to place the transducer along the axis of shaft in such a way. However, transducer will be placed on the bearing position, but the axis should be in parallel position. And what will happen? Horizontal and vertical phase reading. This is also called radial reading. Radial reading usually differ by 0 to 180 degree. So there will be a 0 to 180 degree phase difference. So this is your bent shaft problem. If shafts are not properly aligned, a shaft bending is produced either by an axial asymmetry of the shaft or by external forces on the shaft producing the deformation. Bent shaft. High 1x vibration, you will see 1x vibration in axial direction. That means first harmonic of the turning frequency, it will be most prominent in the axial direction. 2x if behind is closer to coupling. If bend is closer to the coupling. So that means if you are close to coupling and bend is in between, so in that case it may be possible that second harmonic will originate. Axial phase difference in axial direction, if you are going to measure the phase difference, it should be 180 degree out of phase. If these terms will be satisfied, for example, you have find 1x axial vibration or 2x axial vibration and 180 degree out of phase reading, then it may be your bend shaft problem. The frequency spectrum will be look like that, where order represents your frequency and y-axis is your amplitude. Frequency can be represented in 3 units, either in hertz, in cycles per second, cycles per minute, or in orders, okay. What is meant by order? For example, if shaft is running at 200 rpm, okay, then 200 divided by 60, its first order will be at 3.33 hertz, okay, its second order will be at 3.66 hertz, its third order will be at 9.99 hertz, and so on. So this basically represents an order. Bend shaft, 1x peak will be present in the radial direction due to the unbalance. It is also possible to take the phase reading around the shaft, on both sides of the shaft and above and below. We expect all of the readings to be in phase. If on the same bearing position, you can measure above and below or right and left reading, they will be all in phase for bend shaft. And for the different bearing position, if you are going to measure the phase, it will be 180 degree out of phase. For same bearing, it will be 0 degree out of phase, and 1x peak will originate. Misalignment, cocked bearing and short foot. What is misalignment? Shafts are misaligned when their rotational center lines are not collinear. Okay, when the machines are operating under normal conditions. Causes of misalignment: inaccurate assembly, distortion due to forces, coupling phase not perpendicular properly, short foot problem, temperature, growth, or relative position of the components. So there is commonly three types of misalignment found: parallel misalignment, angular misalignment, or maybe the combination of both. In case of parallel alignment, it is produced when the shaft center lines are parallel but not coincident. Okay. In case of parallel misalignment, axis will be parallel. For example, in this case, you can see axes are, this is the center of this shaft, this is center of this shaft, so there will be parallel misalignment. Diagnosing parallel misalignment. In case of angular misalignment, both axes will intersect with each other. There will be intersection at one point, maybe at some distance. Diagnosing parallel misalignment. In case of parallel misalignment, you will see high 1x or 2x in radial direction, maybe 3x and 4x, 5x could also be high. In case of axial, 1s and 2s levels will be high, and phase will be 180 degree plus minus 30 degree across the coupling in the radial direction. So for example, if this is your position of the transducer, then you will see 180 degree or 150 degree out of phase. This is your angular misalignment, where shaft center lines may coincide at one point. You will see high 1x in radial direction, in axial direction, and high 1x and 2x in radial direction, and 180 degree plus minus 30 degree across the coupling. This is your belt misalignment fault, just like two mating shafts. For example, this is your motor end and this is your belt end. It may be possible that these axes are not properly aligned, maybe above or below, just like two mating shafts. Belt drives also show misalignment in both angular and offset directions. In case of belt misalignment, you can see it may be parallel, angular, or combination of both. You can see 1x peak in the radial direction, very important. When you will measure its vibration in horizontal or vertical direction, its 1x peak will not be prominent. But when you will measure vibration in horizontal direction, for example, across the axis of shaft placed on the bearing, then you will see 1x peak more prominent than other. In addition, in axial direction, you will also see 180 degree out of phase. This will confirm that fault is about belt misalignment. If there is a cocked bearing, that is also a form of misalignment, maybe because of the installation practices, short foot it generated because of the installation problem or because of the thermal growth or the short foot problems. So within the spectrum analysis, you have to perform, and you will see that for the cocked bearing there will be high 1x vibration and maybe high 1x or 2x in axial direction, and phase is also a good indicator. For example, you have to measure phase vibration as well. So caught bearing may be because of the inner race or outer race. If it is from inner race, then bearing will wobble with each rotation, and if it is from outer race, then there will be fixed angle relative motion. This is your soft foot problem, where you can see that this end is properly tightened, but this end is loose. So feet of the machine are not flat, so feet not at the same height. It can be checked by loosening and tightening of the hold down bolts. So what will happen? When you will measure the vibration, you will see high 1x peak in radial direction, and even sometime 2x peak will also appear, but in addition 3x peak can also be there. The most prominent, if short foot is in case of induction motor, you will also see a twice line frequency. So twice line frequency that normally originate at 100 or 120 hertz is most common problem of the motors. Because of the short foot it originates, and it appears sometime in the frequency spectrum. So don't worry about it. It normally appears at 100 and 120 hertz. This is about your mechanical looseness. Looseness can be broken down into two main categories: structural looseness or component looseness. Okay. For example, if your whole machine structure is loose, or it may be possible if one of the machine component like bearing is loose, or inner case, outer case faults are there. So there is a part looseness. So component rotating looseness generally occurs when there is a excessive clearance of the components. Rotating looseness occurs due to the improper fitness and excessive clearance. This is the time waveform of the mechanical looseness. You can see the behavior of the time waveform signal, and this is the spectrum behavior of the time waveform. When you have generated the spectrum, you can see on x-axis we have the frequency, and on y-axis we have peak to peak value, and you can see multiple harmonics appear, and it can either stand up to 10x. What does this mean? There is a possibility that if there is a mechanical looseness, then you may observe more than 10 times of harmonics: 1x, 2x, 3x, 4x, 5x, 6x. What does this mean? If shaft is running at 600 rpm, then 600 divided by 60, it will be 10 hertz. That means one peak will appear at 10 hertz, other will appear at 20 hertz, third will appear at 30 hertz, fourth will appear at 40 hertz, and so on. And this behavior is appearance of the harmonics or appearance of returning frequency with multiple harmonics. And even your noise floor can also be raised in case of mechanical looseness. In case of structural looseness, you will only see 1x prominent fault peak in radial direction only, and 180-degree phase difference will be confirmed. So you have seen, in case of the component looseness, there were about 10x harmonics from 1x up to 10x. There may be appearance of harmonics within spectrum, while in case of structural looseness, there is only first harmonics appearance in the spectrum. So only first harmonic will appear in the spectrum in case of mechanical looseness or structural looseness, and it will appear with 180-degree out of phase. Please see the case. Data had been collected on the following fan of several months as part of a routine periodic vibration data collection. During a routine visit to the machine, it was observed that there was a lot of low frequency activity showing around the bearing on the inboard of the fan. So for example, if this is your motor, this is your coupling, and this is your fan. What is meant by inboard and outboard? This is your inboard bearing of the motor, this is your outboard bearing of the motor. Similarly, this is your inboard bearing of the fan, this is your outboard bearing of the fan. That means the bearing that is across the direction of the motor is inboard, where RPM are coming. The nearest bearing is inboard. For example, this was the motor, first bearing was here and second bearing is here. So closest bearing to the coupling is this one. This is your inboard bearing of the motor, and this is your inboard bearing of the fan. Outboard bearing means it will be much away from the coupling position. Okay. Similarly, outboard bearing of the motor will also be away from the coupling position if I am taking it as reference. Okay. So this is basically termed as inboard and outboard. F1H means sometimes we people have to number the position of the bearing. For example, I have numbered as 1, this is 1 position, this is 2 position, this is 3 position, this is 4 position, and I am measuring the vibration in horizontal, vertical and axial direction for first, second, third and fourth position. So F1H means that first bearing and its horizontal direction, and for F means fan. So what does this mean? Inboard position of the fan, that is this bearing, and its horizontal direction, data measurement signal is available in both direction. This is the representation of signal. The multiple plots shown above indicate the change over the time from data taken, and you can see harmonics of turning frequency, the rise of energy as you move further away from the 1Ts. This type of data is common to data of looseness problem as well. Okay, so you can see appearance of 1x, 2x, 3x, 4x, 5x up to 12x harmonics. So basically this is your mechanical component looseness problem. Okay, and its time waveform will be looking like that. The waveform data taken from the particular point for the structural looseness. Structural looseness time waveform data will be appearing like this. Now go for the gearbox analysis. In case of gearbox analysis, gears are commonly used in industry and they are very important power transmission. They are very important for power transmission and speed change. Regardless of the defects that appear, we can diagnose fault using vibration features. So what is the requirement? We need to find, first of all, before going for the gearbox analysis, we should know following parameters. For example, what is the turning speed or what is the input speed? For example, if shaft is running at 600 rpm, okay, then its input speed is 600 rpm. Okay, and if I have used a gearbox that is doing half reduction, that means rpm will be reduced to 300 rpm when it will go for the second shaft after passing through the first pair of gear. Okay, then output speed will be 300 rpm. And what will be gear mesh frequency? Gear mesh frequency formula is number of gears teeth multiplied by input speed of that shaft. For example, if I have a shaft that is coupled with induction motor and at the end of shaft I have connected a gear, that gear is meshed with another gear that is connected to another shaft. Now observe, what is the input speed of the first gear and what is the number of the teeth of the first gear. For example, if number of teeth of first gear are 10 and rpm of first gear are 600, okay, then what you have to do, you have to multiply input rpm are 600 and first gear rpm are number of teeth are 10, then it will be 6000 divided by 60. This will be your frequency in hertz. So your gear mesh frequency will be 100 hertz. Okay, so input speed multiplied by number of teeth of input gear. So what is meant by hunting tooth frequency? Hunting tooth frequency formula is you have to multiply the gear mesh frequency by the common factor divided by input teeth and output teeth, output gear teeth. Okay, so I will show its example. For example, if this is your if this is your input gear, this is your output gear. What does I mean? For example, if this gear is connected with the induction motor and induction motor is moving at 1400 rpm, okay, and suppose this gear have about 26 teeth, then what I have to do? I have to multiply rpm with number of teeth. Rpm are 2400 and number of teeth are 26. Okay, then it will be about 62,400. Divide it by 660 to convert rpm to frequency. It will be 1040 hertz. So its gear mesh frequency will be 1040 hertz. Okay, and if I want to find hunting tooth frequency, I have to multiply 1040 hertz with common factor of the gear teeth and divide it with input teeth and output teeth. For example, if input teeth are 26 and output teeth are 13, then I have to divide it by 26 multiplied by 13 and multiply with the answer with the common factor. Common factor commonly means the most common teeth that mesh during each cycle. So for all number of teeth, the common factors are available within the catalogs. We can easily find the common number of teeth. If number of teeth of pinion gear are for example 30, and if number of teeth of small gear are 15, then I have to first of all find the common factor, maybe 3 or 4 numbers. Then also I have to use these common factors in formula. However, sometimes we people do not use hunting tooth frequency for the gears fault, but it is forcing frequency. Okay, the most important frequency we people use, for example, input speed will give us turning frequency. Okay, for example, if input speed is 2400 rpm, then 2400 divided by 60 will give us 40 hertz. Then I can say turning frequency is 40 hertz. Okay, and output speed, for example, if it is 1200 hertz, if it is output speed is 1200 rpm, then I will divide it by 60 and I will get 20 hertz. Then I will say the output frequency of shaft is 20 hertz. Okay, these are forcing frequencies. So pinion frequency, difference between pinion and gear. The gear that is directly connected with the coupling or induction motor or first shaft is your pinion, and other gear that is connected with the pinion is your gear. Okay, so pinion is identified, for example, the gear which is directly linked with the coupling or induction motor, that kind of gear is known as pinion. Okay, for example, first gear will be pinion and second will be named as gear. So I will name it pinion frequency and gear frequency. Pinion frequency will be the frequency of first gear, gear frequency will be the frequency of second gear, depending upon the meshing. Okay, these are forcing frequencies. Okay, another forcing frequency is gear mesh frequency. How we can calculate it? We have to multiply number of teeth with the input speed. And how I can find the hunting tooth frequency? The formula is there. Okay, for example, you can see here these gears are meshing, and here there will be a existence of pinion or gear frequency, and this frequency is basically your gear mesh frequency that is arising because of the meshing of both gears. And it is about, you can see here, the shaft is moving at 25 hertz. That means pinion frequency will be 25 hertz Yes. Let's see this numerical. For example, this is your gearbox. The gear mesh frequency is simply defined as the number of teeth on a gear multiplied by its turning speed. So what we have to do, for example, if I am going for gearbox analysis, fault analysis, first of all, what I have to do, I have to find pinion frequency, I have to find gear frequency, and I have to find gear mesh frequency. Okay, and at the fourth step, I have to find out the side bands. These 4 points will give me and help me to decide where is the fault within the gear. Okay, first of all, you can see here, this is the input, that means turning speed is coming from here, and this is your pinion. Okay, and this is your gear, which is your output shaft. So input shaft is your pinion shaft and output shaft is your gear shaft. Okay, so number of input RPM and number of input gear teeth. For example, here you can see the input RPM are 1490 and gear 1 teeth are 44. So what I have to do, I have to multiply 1490 with number of teeth of gear, first gear, that are 44. So divide this by 60 to convert it into hertz. You will get 1092.6 hertz. Look here, 1092.6 hertz. This is your gear mesh frequency. This is your gear mesh frequency. Okay, note it down. Okay, what will be your pinion frequency? Pinion frequency will be just 1490 divided by 60. This will be your pinion frequency. It will be about 24.83 hertz. When you will divide this by 60, you will get pinion frequency, and it is about 24.83 hertz. Okay, and what are the number of RPM of the output shaft? I will calculate the number of RPM of output shaft and divide it by 60. It will be my gear frequency. Okay, so first of all, we will find pinion frequency, then we will find gear frequency, then we will find gear mesh frequency, and then we will find gear side bands. Side bands normally appear with pinion frequency or gear frequency. I will help you people to understand how it appears in the spectrum. For example, look here, if there is a gear fault, 1x of the input output speed and intermediate shaft, okay, that means 1x will appear in the spectrum. Gear mesh frequency peak will be present. This is your gear mesh frequency peak. Okay, and side bands, these are your side bands. Side bands actually appear with gear mesh frequency. And what will be the difference of the side bands? It depends upon pinion and gear frequency. For example, here you can see this is your pinion frequency, and there may be resistance of gear frequency in between. Okay, and if fault is with pinion, okay, then you will see side band will appear with the pinion frequency, and if fault is in gear or second gear, you can say output gear shaft, then you will see the side bands will appear with the gear side bands frequency. Okay, for example, if pinion frequency is appearing at 24 hertz and gear frequency, that is the frequency of output shaft, is appearing at 12 hertz, that means half reduction is here. Okay, pinion frequency 24 hertz and gear frequency is 12 hertz, then when we will see spectrum, we will see one pinion frequency, one gear frequency, that will be about here, and we will see a one gear mesh frequency. Okay, now it depends upon fault. Either fault is in pinion or gear. For example, if fault is in pinion, then side band will appear with 1 xp. What does this mean? Gear mesh frequency plus minus 24 hertz. Okay, if gear mesh frequency is, for example, if gear mesh frequency is 1000 hertz, then lower this side band will appear with 1000 minus 24 hertz, and this side band will appear with 1000 plus 24 hertz. Similarly, this band will appear with 1000 minus 2 multiplied by 24 hertz, and this sideband will appear with 1000 plus 2 multiplied by 24 hertz. In the same way, these closer sidebands are called first sidebands. This is your second sideband on left and right side. Similarly, third, fourth or fifth sidebands can also appear. Okay. Similarly, if the fault is in gear, for example, if fault is appearing at 12 hertz, okay, then these sidebands will appear with difference of 12 hertz. These sidebands will appear with the difference of 12 hertz. Now it depends upon the gear mesh frequency, amplitude, and the sideband's amplitude as well, how much the fault is critical. You people have to decide depending upon the gear mesh frequency. If fault is within the gearbox, you will see that gear mesh frequency will originate within the spectrum. First point. Now if fault is in pinion, then you will see sidebands originated across the gear mesh frequency with the difference of pinion frequency. Okay, and if fault is in gear, then you will see sidebands that will appear across the gear mesh frequency with the difference of gear frequency. Okay. In addition, you people will see that if fault is in pinion, then you will see high XP peak as compared to XG peak. XP means pinion frequency peak, XG means gear frequency peak. If fault is in pinion, then amplitude of pinion frequency will be higher than the gear frequency, and if fault is in gear, then amplitude of gear frequency will be higher than the pinion frequency, and it will appear here because they will be appearing at lower RPM. So this is how we can decide about the fault. So if this kind of problem comes in your final exam, then first of all you people need to find pinion frequency, then you need to find gear frequency, then you need to find gear mesh frequency, and then you have to find where sidebands are appearing. This will help us to identify is there any existence of fault in the gearbox. If it is fault in the gearbox, then where is the fault? Fault is in pinion or gear. After this identification, we also have a vibration analysis spectrum technique from where we can identify either, for example, if we have identified that fault is in pinion, then what kind of fault it is. It is eccentricity fault, there is the crack on the pinion, there is a broken tooth on the pinion, there is the eccentricity problem, there is the backlash problem in the pinion. So all of these faults can also be identified depending upon the gear mesh frequency. You will see that harmonics of gear mesh frequency, for example, if it is appearing at 12 hertz, then there may be its second harmonic appearing here at 24 hertz with sidebands, and maybe at 36 hertz as well with sidebands. This will help us to decide which kind of gear fault it is. For example, in case of spur gear, you will see higher gear mesh frequency in radial direction, and in case of helical gears, you will see higher gear mesh frequency in axial direction. The time waveform of the gears will be like this. Time waveform is very powerful analysis tool for attempting the diagnosing of gear faults. Gears can produce different types of waveforms, the one shown below. As the defective teeth come into mesh with the noise generated increase and increase in amplitude in the vibration data. So G's value basically represent acceleration amplitude, and this is SS is your revolution, and you can see for each revolution there will be one impact, and that will appear with higher amplitude, and it will appear at particular gear mesh frequency, and from this we can identify there is a gear mesh frequency fault. Okay, and this is how we can identify fault from the spectrum. Now if there is a gear eccentricity or backlash fault, then you will see either one first harmonic of gear mesh frequency is more prominent, and third gear mesh frequency harmonic is more prominent if the fault is in case of eccentricity and backlash. Okay, backlash may also excite the gear natural frequency. This is yes, very important thing. For example, gear mesh frequency, this is first harmonic, this is second harmonic of gear mesh frequency, this is third harmonic of gear mesh frequency, this is your pinion frequency, this is your another frequency, short frequency, alternate frequency. Okay, if the fault is of backlash, then there may be a problem that backlash may result in the resonant position of that gear. So what will happen when resonance will occur? Gear will resonate when it will try to vibrate at its natural frequency. Okay, when excited frequency will try to approach natural frequency of gear, then its natural frequency will try to originate. So gear natural frequency means, if gear natural frequency originates, that means that there is a backlash problem as well. And again, how we can find gear natural frequency? It is very simple. It can be found out from the different analytical models as well. Also, we can identify it from the experimental data or the bump test. Bump test can be performed using the rubber, using by striking the machine component with the hammer that have a rubber tip on its one end, and that tip may be of the cork material or wooden material, or maybe of the stiffer material. So in this way we can excite low frequency, medium frequency and high frequency peaks within the machine. So if we are successful in exciting the particle frequencies of the machine with the excitation force, that is excitation harmonic force applied to the machine component, then structure will try to provide peak energy that will be originated from the components, and that energy, peak energy, will be originated from the machine components at their natural frequencies, and this will be basically your resonant frequency. So this is how we can identify different natural frequencies of machine components as well. So when your gears are properly misaligned and they are not properly aligned, so what will happen? The misalignment will result in multiple harmonics of gear mesh frequency, and again sideband will appear with either 1x or depending upon either fault is in pinion or gear. It is therefore very important to set your frequency F max high enough to see these frequencies. I will show you people CSI 2130 and 2140 analyzers, and you will see before data collection, first of all vibration analyst should properly format the input data, where there will be what will be the input of the machine, what are the input RPM, what are the gears and pinion number of teeth, and similarly what are the output RPM, and depending upon this we can guess what will be the gear mesh frequency. For example, if we people know, for example, if machine is running at 1000 RPM, then normally we people use the F max for 3000 RPM. That means we have to measure data for 3 times higher than that of the RPM of machine. So this will help us to capture high frequency fault as well. If we will only measure up to twice of the RPM, then what will happen? It may be possible that high frequency faults may be missed and it will not appear in the spectrum. So setting resolution of the signals is very important, and one should know how to set the frequency resolution, because this course is very limited and it will go in detail. If you will, I will try to explain what is meant by resolution and how we can fix the problems. Normally we keep the formula. For example, what is your first gear mesh frequency? Multiply it with 3. Okay, keep that frequency of the frequency analyzer. For example, if first gear mesh frequency is appearing at 1500 Hz, then its third gear mesh frequency harmonic will appear at 4500 Hz. Okay, then I have to use the F max of 4500 Hz. Even I know that first gear mesh frequency will appear at 1500 Hz, but I need to capture at least 3 gear mesh frequencies. So that's why I need, if I will use 2 F max, then what will happen? 2 gear mesh frequencies will appear and third will be missed, and I may identify fault within the gear, but I will not identify either fault was for backlash problem or misaligned gear problem or eccentricity problem. So for the proper identification of the gear fault, you need to measure the data for 3 times of F max at least. You can see if there is cracked gear or broken tooth, then for each cycle there will be a one bump, okay, string, and that string will appear at 1x. Okay, for example, if turning RPM are 1400 RPM, then 1400 divided by 60, it will be about 23.33 hertz. What does this mean? The 1x frequency will be 23.33 hertz. Okay, so if we have cracked gear, then gear mesh frequency will appear with sidebands of 1x. A cracked or broken tooth will generate a high amplitude peak at a turning speed. So this 1x amplitude will be very high. Gear native frequency may generate. So gear native frequency may arise in this case with sidebands. There will be a sideband of the turning speed of that gear. This is the numerical problem that was given in the previous final paper of mechanical engineering. What are the different types of maintenance practices followed by the industry? I have discussed in detail. Explain briefly any 2 types of problems faced by rotary machines in the process industry. Again, I have explained them in detail. The third problem was about the machine transmits power through a double spur gear system. Okay, that means induction motor consists of pinion and gear transmission system. Pinion is actually connected with the coupling shaft and gear is connected to the second shaft. Okay, the pinion is your first gear and output shaft gear is your second gear. The pinion is running at the motor RPM of 1223 and having number of teeth 12. So number of pinion teeth and its RPM are given. So this is the one of the given information. In addition, while the large gear is meshed with the pinion gear having a gear ratio of 0.5. So gear ratio is provided for the second gear. Okay, so what will happen if input RPM are 1223, then what will be output RPM? Because half reduction is there, so 1223 multiplied by 0.5, output RPM will be 611.5 RPM. Okay, then the vibration spectrum of the spur gear system has been shown below. Please identify, compare with the spectrum and then identify which gear is damaged. Problem was we have to identify either pinion is damaged or gear is damaged. Okay, we have 2 gears, gear 1 and gear 2. We have to identify either gear 1 is damaged or gear 2 is damaged. Okay, gear 1 RPM and number of teeth are given, gear 2 RPM are given. Okay, now what we have to do first of all? First of all, I have to find pinion frequency. What will be XP? For XP, I have to divide 1223 by 60. So 1223 divided by 60, it will be about 20.38 hertz. Okay, this is your pinion frequency. Okay, and what will be your gear frequency? Because there is half reduction, so half of 1223 RPM are basically, and when we will divide it by 60, it will be about 10.12 hertz. Okay, so pinion frequency is 20.3 hertz, and gear frequency is about 10.2 hertz. Okay, so we have find out pinion and gear frequencies. This was our first step. What will be second step? In second step, we have to find gear mesh frequency. What is gear mesh frequency in this case? Number of RPM of first gear and number of teeth are given. So simply multiply number of teeth, for example 12, with its RPM, that is 1223, and divide by 60 to convert into hertz, and it will be 244.6 hertz. So gear mesh frequency is 244.3 hertz. You can see here. Okay, so this is the practical signal that is obtained from the gear system, and you can see that gear frequency gear mesh frequency is appearing at 244.3 hertz, and this is your gear frequency 10.39 hertz, and here there will be your pinion frequency, but its amplitude is very low. Pinion frequency amplitude is very low, while gear frequency amplitude is higher. This is one point to be noted. Please note down that pinion frequency amplitude is higher than the please note down that gear frequency amplitude is higher than the pinion frequency. Second point, we have a gear mesh frequency that is originating at 244 hertz. Third point, please note down that gear mesh frequency amplitude is very high and it is appearing with proper sidebands. Now we have to check what are the sidebands appearing with. For example, you can see 244.10.3, it will be about 254.7, and similarly 244.3 minus 10.3, it will be about 234.53 hertz. Okay, so that means this sideband and this sideband, it is appearing with xg or gearing frequency. So gear mesh frequency plus minus xg. So sidebands that are appearing with gear mesh frequency are basically coming from gears, not from pinion. So that means there is fault within the gear of the transmission system. Okay, this is one point, because sidebands appeared are coming from the gears. Second gear, sidebands are coming from the second gear that are appearing with the gear mesh frequency. So this is one identification that fault is present within the gear, second gear. Okay, what is second point? Second point is that gear frequency is occurring at 10.39 hertz and it have higher amplitude than the pinion frequency that actually occurring at about 23 hertz. Okay, so what does this mean? That is actually pinion frequency is actually occurring at 20.38 hertz. So what does this mean? Amplitude of gear frequency is higher than amplitude of pinion frequency. So that means there is some kind of fault within second gear as compared to first gear. So these are two spotting points in our case. So this was the requirement of the problem. You can easily say that within the power transmission system, it is clearly identified from the given calculation and given values that gear mesh frequency is appearing at 244 hertz and corresponding sidebands are appearing at 234 and 254 hertz. Not only this, gear frequency is appearing at 10.39 hertz, have higher amplitude than the pinion frequency, and sidebands are also appearing with the second gear frequency. So that means there is a fault in the second gear. Okay, now this was the requirement of the problem. However, in case of the higher analysis, you people may be asked that what kind of fault it is within the gear. For example, either its teeth are broken, either there is a backlash problem, eccentricity problem, misalignment problem. But it is for higher case studies. I am not going to give you a side time of tough problem within exams. Okay, so this was the problem that was given within the exam, and these were the provided formulas. These are the gear fault frequencies, and formulas were also given. Gear mesh frequency equals number of teeth multiplied by turning speed. How you can find sideband frequency? You can find sideband frequency as number of teeth plus minus 1 multiplied by turning speed. Okay, for example, if number of teeth of the first gear or second gear are provided and you have the corresponding turning speed, you can also find the sideband. And how you can find the gear ratio? By the ratio of number of teeth of input gear to number of teeth of output gear. And how you can find the speed, output speed? You can find the output speed by multiplying gear ratio with the input speed. Okay, these were the provided formulas in paper, and these were the extra formulas that were provided to you people to make you confused. These formulas will not be used in this problem. Okay, however, these are the fault frequencies that appear in case of bearing. So bearing have inner race frequency faults, outer race frequency faults, cage frequency faults, or rolling element frequency faults. So if we know these parameters or these variables, so we can easily calculate these kind of fault frequencies within bearings as well. Okay, solution of the above numerical is here. Please pay attention. This is your solution. Input or turning speed is 1223, and in order to find first gear or pinion frequency, you have to divide it by 60 and it will be 20.4 Hertz. So this is your pinion frequency. This is your pinion frequency. Now first gear teeth are 12 and frequency is also calculated, so we can find gear mesh frequency as can be found as 1223 multiplied by 12 teeth divided by 60. It will be your gear mesh frequency. Okay, and how you can find gear frequency? You can find gear frequency because there was given that it is the half reduction. So if it is half reduction, then if first shaft RPM are 1223, then we have to divide 1223 by 2 and then divide it by 60. So it will be half of this, that means 10.2. So gear frequency will be 10.2 Hertz. Here you can see. So large gear frequency is 10.2 Hertz and small gear frequency is 20.4 Hertz. First gear is small, second gear is large. Small gear is also called pinion, large gear is also called gear. I am naming it as first gear frequency, this is your second gear frequency. Okay, and these are your corresponding number of teeth. How you can find the number of teeth of large gear? Okay, as provided in the formula. And gear mesh frequency we have already calculated, multiplying the number of teeth of first gear with its RPM. This will be your gear mesh frequency. Okay, and this formula for sidebands was also given. For example, number of teeth minus 1 multiplied by its RPM divided by 60. So it will give you a sideband. So plus minus 1 means 1 on front side and 1 on below side. One sideband will appear on the right side and one sideband will appear on the left side. Okay, so you can see we have calculated the sidebands. Sideband are appearing at 234.6 Hertz and 255 Hertz, 234.6 Hertz and 255 Hertz. So you can see 234 Hertz here, 255 to 54 Hertz here. Okay, so that means the fault was, this is the reasoning that is very important. This was all about calculation, how we can find pinion frequency, how we can find gear frequency, how we can find gear mesh frequency, how we can find second gear number of teeth. Okay, and how we can find the corresponding sidebands. After this we have to provide the reason. Since both sidebands left and right of both gears have been appeared in the spectrum and matches with the frequencies calculated theoretically, but the spectrum shows RPM peak of only larger gear shaft 10.2 Hertz, that is about second gear frequency, and in spectrum 10.39 Hertz. So this indicates, see here, 10.39 Hertz. This peak is of higher amplitude. Okay, gear frequency is higher than pinion frequency. So this indicates that fault is in the second gear or larger gear. Okay, so you can see when we have calculated the sidebands, then we have seen that sidebands are appearing with both pinion and gear. Okay, but gear mesh frequency was of higher amplitude and we were not approaching a particular solution. But when we have find out the pinion and gear frequency and we have find out the amplitude of the gear frequency higher than the pinion frequency, and this have helped us to decide that fault is in the second gear. So this was the very interesting problem I hope you people have enjoyed that. I will upload its solution as well. So this is a numerical problem we have discussed in detail, that was appeared in the previous exam. These are your belt drive faults. In case of belt drive faults, belts are the most important and most common low cost way to transmit power from one shaft to another. Ability of belt to transmit power depends upon belt tension, friction in between, arc of contact and speed of belt. So belt frequency will also having these variables within its formula. So you can see belt frequency can be calculated using this formula, where all of the variables are denoted here. You can see this is the pulley turning speed, this is your pulley pitch, circle diameter, and this is your belt length. So when you can calculate all of these variables, and in this way you can find the belt frequency. The fundamental belt frequency can be calculated using this formula. Okay, and if belt is not plain, it is timing belt, it will have a number of teeth, then you have to use this formula: pulleys turning speed multiplied by number of pulley teeth. It will give you timing belt frequency. Okay, now I am going to start rolling element bearing analysis. So a bearing is a machine element that constrains relative motion between moving parts to only in the desired motion. Load is transferred through the rolling element bearing, such as balls, straight and tapered cylinders and spherical rollers. Rolling element bearings have specific bearing failure modes that can be observed in the spectral and waveform data. You will see that bearing does not fail in certain moment. The fault appear in different stages. For example, all of the bearing faults are high frequency faults, but they appear in stages. For example, when high frequency fault will appear, then its first stage will be appearing in a particular zone. Then we will see a second stage appearance of the frequency spectrum. Then we will see third stage appearance of the spectrum, how it will be looking. So you will see time by time the frequency peaks shift towards the left side of the spectrum. So this indicates that particular stage of the bearing failure, and higher is the stage of failure, higher is the critical stage of your bearing. So depending upon the stage of your bearing, you can calculate the remaining life of the bearing as well, and you can provide in conclusion or recommendations that please replace your bearing within XYZ days, because your bearing is currently under the second or third stage of failure. Okay, or sometime they can also ask, please mention the stage of failure of bearing as well. So proper vibration analyst always mention if there is a proper bearing fault, then which stage it is going with. Why do bearing fails? As a vibration analyst, it is your job to simply detect the fault. Okay, if bearings were correctly specified, transported, stored, installed, lubricated and operated, then they would provide reliable service for many years. But actually this does not happen. Okay, there is always installation error, lubrication error, contamination within the grease. So different contamination particles provide a frictional forces. Also there is a static dynamic loading, overloading is also issue. thermal growth is also a problem. So all of these problems will result in the bearing failure. Almost all of the factors are not taken care of. As a result, bearing only 10% of their design lifetime. So what does this mean? If within catalog the total life of bearing is 5 years, then you can estimate that it can only survive for 10% of the actual life. Okay, if we are not going to take care of the above factors. When bearings fail, we may experience sudden downtime and secondary damage and also high labor costs as well. So how bearing fails? This is the pie chart. 36% failure of bearing is only because of the lubrication. If there is no proper lubrication, there are also different certifications that are concerned with the lubrication of bearings, what type of lubricant we have to use for a particular bearing, and how we can increase the reliability of bearings. These certifications also have different levels. I will suggest you people to go with these certifications as well. Fatigue failure is 34% problem, dynamic loading, static loading as well. Okay, 16% failure is because of the poor installation, and 14% failure is because of the contamination of particles. So what are the possible bearing defects? You can see this is your outer race, that is the external bypass frequency. You can see when you can hold this part static, then this part can move, and the frequency of this outer ring is basically outer race, and it can be represented as ball pass frequency outer race. This is your inner ring, and its frequency will be ball pass frequency inner race. Okay, please keep in your mind. This is your fundamental train. Okay, there is a proper train cage that is held in between in order to keep the balls in position. Okay, if you people have bearing, please open that and you will see a proper cage in which balls are placed. So that cage is also moving. Keep in your mind, every revolution part of the bearing will have its fundamental frequency. Okay, outer part can also move, so it will also have a frequency, that is ball pass frequency outer race. Inner part can, or inner ring can also move, so it will have a ball pass frequency inner race. Okay, similarly cage can also move, so it will have a train frequency, train cage frequency, or fundamental train cage frequency, FTF. Okay, similarly balls can also spin or move, so they will also have a ball spin frequency. Okay, so shafts move, gears move, or either belt drives, or even other elements as well. Every component will have its own particular frequency depending upon its RPM. Okay, so in case of bearing, how many frequencies are important? 4. First frequency is ball pass frequency outer race, that is for the outer ring. Second is ball pass frequency inner race, that is for the lower ring. Third is third is cage frequency or fundamental cage frequency, that is for the moving cage. And fourth is for the spinning balls, that is ball spin frequency. So all of these frequencies have measured formulas. They are theoretically derived and analytically proved. So you just have to put the values of the variables within the formulas, and you can easily find out the BPFI, BPFO, FTF, and fundamental train frequencies or spin frequencies. Okay, so what you need to know, for example, within industry, if some bearing have a problem, or you people already know because catalog is provided, and you people are always told that we are using the bearing used for this position is with SKF XYZ number. Okay, the number is provided to you people. So if the bearing type is SKF, you can go to internet, you can open the website of SKF, and if you people know that it is anti-friction ball bearing or deep groove bearing or cylindrical bearing, then you have to provide the number of the bearing. When you will provide the number of the bearing, then he will automatically give you all of these frequencies. Okay, and if you people know the number of the bearing, okay, if you people are not well familiar with the number of the bearing, which bearing is used, then you people should know the following variables. For example, what is the total number of balls? Okay, for example, here in this case you can see 1 2 3 4 5 6 7 8 9 10 balls. 10 balls are here in this case, so NB will be 10. Okay, then you have to identify ball diameter. Okay, it will be BD, you should know. And third parameter you should know is pitch diameter, that is from center of one ball to center of this. So pitch diameter, that is from one end to other end center, so it is very important, you should know. Fourth point is contact angle between outer race and inner race. For example, either 30 degree, 40 degree, 50 degree, you should know. These are 4 important variables. And when you will have number of balls, ball diameter, pitch diameter and contact angle, then you just have to put these variables in these analytical formulas, and by this you can find inner race rotating frequency, outer race rotating frequency, fundamental terrain frequency and spinning frequency. Okay, so inner race frequency normally appears at 0.33x to 0.48x. So that means it occurs in subsynchronous range. For example, less than first harmonic. What does this mean? For example, if motor is running at 100 Hertz, okay, then its fundamental terrain frequency can appear in between 33 Hertz to 48 Hertz. Are you getting my point? If motor is running at 100 Hertz frequency, then its fundamental terrain frequency can appear between 33 to 48 Hertz, and for outer race it can appear in between 52 to 67 Hertz. So you can see outer race range is higher than the inner race. Parameters are same, variables are same. Those 4 variables are required, and you can easily find FTF for outer race and inner race. Okay, this is ball spin frequency. Again, previous variables I have told you people you should know. You can easily find ball spin frequency. Ball spin frequency will appear 1.9 times of the turning frequency and 5.9 times of turning frequency. That means that it can appear in between 1.9 to 5.9 times of the turning frequency. Okay, so 2 times of ball spin frequency will be dominant due to the spall on the rolling element come in contact with the both inner race and outer race. Sometimes there may be a problem that ball spin and it come in contact with the inner race one time, and on the other hand it may come in contact with the outer race as well. Okay, so it may be possible that ball spin frequency can appear 2 times of its ball spin frequency as well. For example, its second harmonic can also appear as well. So this was about ball spin frequency. So it actually tells us the frequency of revolution of each ball or roller. So this is ball pass frequency in the race. This is the given formula. Required parameters are ball dia, pitch dia and contact angle and number of balls. Again very simple, and its spectrum will appear or originate in between 6.3 to 13.8 times of harmonic frequency, okay, or turning speed. So in between 6.3 and 13.8 times of turning speed, ball pass frequency in a race appears. So these are very important points that are always provided within the catalog, and vibration analyst can easily identify the fault. And for ball pass frequency outer race, that range is given below, between 4.2 to 11.3 Hz times of the turning frequency. Okay, now we need to find the stage of the bearing fault. For example, this is your stage 1. You can see that this is your turning frequency 1x, and this is your frequency axis, and this line is showing 1 kilohertz, this line is showing 5 kilohertz band, this line is showing 40 kilohertz band. Okay, So you can see 1 kilohertz band is empty, 5 kilohertz band is also empty, 40 kilohertz band is also empty. Only only terminal frequency is appearing with 1x. Okay, so this is your stage 1 bearing fault. If this appears, that means your bearing is at stage 1 failure. This is your second stage failure. In second stage, in between 5 kilohertz and 40 kilohertz, proper spectrum will originate, and you will see that there is a proper appearance of the fault frequencies in between 5 kilohertz and 40 kilohertz zone. Okay, so this is your second stage failure. So in case of first stage failure, you people have observed no frequency band. Why? Because that frequency band will be lying above 40 kilohertz. Okay, so normally we measure under 40 kilohertz, we do not need to measure above 40 kilohertz. If it is coming under 40 kilohertz, okay, then it will be second frequency fault, and if it is not appearing under 40 kilohertz, then that means it will be your first frequency fault, a first stage fault. Okay, so higher is the band of the frequency, higher should be the sampling rate of your measuring sensor, and higher will be the f max or resolution, f max resolution of the measuring instrument, and it will be very expensive instrument. This is your second stage failure. This is your third stage failure. In third stage, you will see that spectrum will originate between 1 kilohertz and 5 kilohertz, and bump will appear in between 5 kilohertz and 40 kilohertz, and below 1 kilohertz you will see a proper 1x peak, ball pass frequency outer edge peak with sidebands of 1x, and second harmonic of ball pass frequency with its sidebands. Okay, so this will show you people that failure is in third stage. This is your fourth stage failure. In fourth stage failure, you can see bump lies in between 20 and 40 kilohertz, small spectrum appears in between 1 kilohertz and 10 kilohertz, and large harmonics of turning speed will appear in between 0 to 1 kilohertz. Okay, you will see that large number of harmonics of turning frequency will appear in between 0 to 1 kilohertz. So this will indicate that it is fourth stage of failure of the bearing. So what does this mean? This was your first stage, and it is recommended as very high frequency range. Okay, first stage is very high frequency range. Why? Above 40 kilohertz. Okay, this is not very high, but it is only high frequency. Second stage is high frequency that appear between 5 kilohertz and 40 kilohertz. Second stage failure is medium frequency that appear here, and ball pass frequency and its harmonic will appear here. Okay, and fourth stage is low frequency. So that means harmonics of the turning frequency will appear from 0 to 1 kilohertz, and between this band and this band it will also appear. So these are the normal signatures of different stages of the bearing. Now it depends upon the vibration analyst, whenever he is going to collect the vibration data, and he will have to apply the proper enveloping signals processing techniques and proper filters and enveloping techniques that will help him to identify which stage of failure is this bearing going with. Okay, please see below. Here you can see in between 0 to 500 hertz, you can see that ball pass frequency outer race, this E is basically nothing but frequency of ball pass frequency outer race. This ball pass frequency outer race is appearing here, 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 and here, and here. Okay, that means multiple harmonics of ball pass frequency are appearing in between 0 to 500 hertz. So the fundamental frequency is ball pass frequency outer race, harmonics from low to high frequency. Okay, so How we can identify that fault is in inner race, outer race, or whatever? For example, you have created a time waveform. I will draw its spectrum, and from spectrum, then I will analytically solve the given formulas. I will find out the ball pass frequency inner race value, ball pass frequency outer race value, fundamental turn frequency value, and spinning ball spin frequency value, and then I will match the peaks, which peaks are originated and how many times. And in software packages they have built in calculation formulas, and when you will put the bearing number, then he will automatically identify that which fault frequency is originating and how much harmonics are originating with how much amplitude. So you can see that the scale will appear, and scale is showing me that in this spectrum ball pass frequency outer race harmonics are appearing with higher amplitude. This means fault is in outer race. So this all can be done in online monitoring. Okay, I just have to put my accelerometer that is connected with the multi-channel analyzer CSI 2130 or 2140. I have to put the accelerometer in axial, vertical, and horizontal direction, and I can collect the data. On the spot, I can see time waveform and frequency spectrum as well, while I can also record the data, and I can do the signal processing in my office as well. Okay, this is another spectrum that you can see, and here you can see that ball spin frequency peaks are appearing with higher harmonics. Okay, so when ball spin frequency was calculated, it was found that these peaks match with ball spin frequency. So they have characterized that there is a fault in rolling element ball. Why? Because ball spin frequency is appearing, that means there is a fault within the ball. Maybe there are some cracks or rubs appear within the balls or so on. This is another signal that is obtained from the practical analysis. Here you can see that fundamental train frequency is more prominent. These frequencies are more prominent than others, and when these frequencies were matched, it was found that these green frequencies belong to some other component, and these red boxes are showing this one, this one, this one, this one, this one. These are all frequencies, and these frequencies actually belong to fundamental train frequency, FTF, fundamental train frequency. So when fundamental train frequency was calculated, it was found that it appears at 0.4 order, as you can see in subsynchronous region. I have already explained in the theory that fundamental trace frequency always appear in subsynchronous region. For example, region that is below 1x is subsynchronous region. So this is how we can easily identify which bearing fault is originating. Here fundamental trace frequency and its harmonic were very prominent, so that's why fault was in fundamental trace frequency. This is the typical time waveform of the bearing. As the bearing becomes defected, then the amount of noise force generated as the rolling element impact the defective area increase. This can show significant G levels in the time waveform. This value is trended in the software as the peak to peak value. This data is taken from a pump with a damaged bearing. So you can see peak to peak value is very high, and it is about 24.47, and crust factor value is also very high, 2.38. Some of the statistical parameters like peak value, peak to peak value, mean value, RMS value, crust factor value, Curtis's value, standard deviation, and fourth standard deviation value. So all of these values are very helpful to identify faults for transient signals or high frequency faults. For pumps, fans, and compressors, again, pumps, fans, and compressors can all suffer from the classic fault conditions: imbalance, misalignment, bearing faults, and looseness. Some faults are unique to these items. For example, blade pass frequency. Blade pass frequency will be in case of a pump Blade pass frequency is a pulsation force that is generated in pump, fans and compressors. It is common in pumps, fans and compressors. Forces are generated by the pressure variation as a rotating blade vane or a lobe passes and it rotates. The stationary component creates a non-uniform flow disturbance in the fluid or gas. Volutes, cutwaters and diffusers vanes. So how you can find blade pass frequency? Very simple. You have to multiply turning speed with number of blades or turning speed with vanes number, or you have to multiply turning speed with the number of lobes, or you have to multiply turning speed with the number of pistons. It is very normal for this peak to be present in the spectrum. What does this mean? Blade pass frequency, if you are using pump, fan, compressor within your system, then it may be possible that blade pass frequency will appear in your frequency spectrum. Okay, you will simply multiply number of blades or number of vanes or number of lobes or number of pistons with their turning speed and divided by 60, and required will be the frequency of the blade pass frequency, and it will be present in your spectrum if your system consists of these elements. Okay, and it may have a certain harmonics as well. You can see this was the turning speed of the vane pass, and you can see vane pass frequency can be found by multiplying number of vane by its turning speed, and you can see this is first frequency, first harmonic of vane pass frequency, this is second harmonic of vane pass frequency, and it can also appear with the side bands of 1x or 2x depending upon the fault. So now I will talk about the resonance and natural frequencies. All the machines and structures have a natural frequencies. If well designed, natural frequency lie dormant. If natural frequency excite, they resonate. Vibration levels are amplified, fatigue and damage follow. Up to 50% of the failure is because of resonance. You need to understand resonance in order to become a successful vibration analyst. How to detect resonance problems? Look for springs of unusual failure. You should consider the resonance as a possible cause. Examples: you can see broken welds. Often type of welds are broken. You can see cracked or leaked pipes, premature machine failure, broken or cracked shafts, foundation cracks. These are faults are because of the resonance. Okay, signs of resonance: you will see unusual high peaks amplifiers. You will see much higher directional vibration in one axis over the other. For example, when you will check the vibration in vertical, horizontal and axial direction, and you will see that in one of the direction vibration amplitude will be very higher, either in vertical, horizontal or axial direction. You will be shocked why this vibration amplitude is very high. For example, if it is 0.2 millimeter per second velocity amplitude in horizontal direction, in vertical it may be 0.9 millimeter per second, in axial direction it may be 20 millimeter per second. There is no comparison of 20 millimeter per second with 0.2 and 0.8 millimeter per second. So that means such a higher amplitude is because of resonance. So you will see haze tracks and humps that will appear in spectrum, changes in the amplitude with change in speed. So you will see that resonance problem normally occurs at particular RPM, because it always occurs when forcing frequency will try to approach the natural frequency of the system. So when RPM will differ, for example, if one structure is having very high amplitude at a certain RPM, then first technique to identify resonance is the measure of amplitude. If amplitude is very high, there is a resonance. How you can identify resonance? In second step, you can change RPM. For example, if steam turbine is running at 10,000 RPM and showing very high amplitude, then please slow down its RPM to 8500 RPM. You will see that there is an abrupt drop of vibration amplitude, and below at each RPM vibration amplitude will be very small. Then that means at 10,000 RPM there was some resonance problem. Okay. So example of haystacks and humps, you can see that 3x has been amplified. So here you can see this is your 1x peak, this is your second x peak, this is your third x peak. Okay, 1x peak amplitude is only 0.1 or 0.15, while amplitude of 3x peak is very high as compared to 1x and 2x, for example more than 0.35. Not only this, you can see this hump that appear between in this zone. Your signal will move up from the mean line and it will try to generate a hump. All of the vibration from 30 Hz to 65 Hz has been amplified. You can see from this point to this point, vibration amplitude have been increased too much. Not only this, signal is trying to fly away from the mean point or mean line. Similarly, here you can see the vibration signal is on the mean line. Here vibration signal is on the mean line. Here vibration signals are moving away from mean line. So here there is a resonance. Here again you can see this zone consists of a vibration signal that is moving away from the mean line and also have a very high vibration amplitude. That means the resonance problem is there. Okay. Bump test. It is one of the very important tests to find out the natural frequency of the different components of the structure. Striking a machine structure injects energy at all frequencies. Soft mallet injects more energy at lower frequencies. Metal bar will inject energy at higher frequency, and wooden bar or timber wooden bar which will inject energy at the medium frequencies range. So what will happen? It can be done when machine is running. Okay, for example, your machine is running and you can easily hit any of the bearing position, and your sensors are placed on the different position of the machine, and in this way you have excited the machine, and you can excite the machine with different ways. Either you can excite your machine for the low frequency fault or medium frequency faults or high frequency. For example, if some of the machine components have low frequencies, some of machine components have medium frequencies, some have higher frequencies. Okay, if you want to find the natural frequency of these components, you need to excite these components at the corresponding excitation or harmonic frequency. So I will try to excite that machine with either mallet or by use of the bar. So I will strike a mallet on the first step for the low frequencies, then I will strike the metal bar for the high frequencies, and I can also strike the wooden timber for the medium frequency of the components. So what will happen? Be careful not to damage the machine. You have just to strike the component. When you will hit the component, keep your vibration force not above the certain limit. It can be done when machine is running. Okay, so this is the beauty of the bump test, that it can also be performed in the running of the machine while it is in the functional form. So here you can see low frequency peak is here, medium frequency peak is here, and high frequency peak is also there. Okay, 0 to 50 Hz. So you can see when you will excite the structure with particular forcing frequency, then the structure components will dissipate energy, and they will try to dissipate energy at the corresponding natural frequency. So in this way you can find the natural frequency of the corresponding components, either low frequency faults, medium frequency faults, high frequency faults. Because first when you will find the natural frequency of the low, medium and high frequency components, then you can identify at what frequency or what frequency this machine can resonate. Okay, so whenever your machine is running at, for example here in this case 10 Hz, sorry, it is about 5 watts, or at this peak, or at this peak, or at this peak. So whenever your machine is running on these peaks, there is a problem that your structure will resonate. So try to keep RPM of your system or forcing frequency of your system should be away from these natural frequencies of the structure. So this was the level 2 course I have discussed in the video lecture. I have discussed all the problems in detail, different faults for vibration analysis. Inshallah, in coming class, I will also discuss some other cases, for example, thermography cases and some other vibration cases. That will be case studies, and I will also show you people and the vibration analyzer as well, and different signal processing techniques. So please stay with me. The above portion I am showing you people will not be part of your exam. Till now, the things we have discussed in detail are part of your exam, okay, but the things we will discuss after that or onward will not be part of your exam. I am just showing these things to you people just to make your concepts very clear, so that you people can perform very good at industrial level, okay. So previous course I have shared with you people, it will be involved in your final exams, and this is an extra material that I am provided to you people in order to make you people very much, it will be very helpful for you people for understanding by adding the additional data. For example, you will see I will look into thermography, acoustic emission techniques, NDT techniques, and small introduction to vibration analysis as well. And the references of the data again go to Mobis Institute, CVCM, Sumiko Technologies, Pakistan. I am special thankful to them. So major lecture will be on the failure mode analysis in case of bearing, belts, gears, pumps, and the case of resonance. So you people will see how bearing defects, they are very helpful for you people, for example with respect to final exam as well, okay. So we will be only dealing with roller bearings. Belt defects are also important, gear defects are also important, pumps, fans and compressors, resonance and electrical defects will be discussed. So these are your structures and machines. You can see the importance of grease within the power transmission system. They have proper grades, and because the grades are decided according to the availability of material to transmit the torque, so proper viscosity and all of the mechanical and chemical properties are balanced. So different grades are decided according to different temperature levels within different zones of the country. It is well said, reliability and maintenance are tools. I will say reliability and maintenance are very important tools in the manufacturing survival toolkit. By all polling. So you people know how vibration travels. If we will assume motion transmitted is in simple harmonic motion, then we can measure the sine wave amplitude versus time domain, and we can measure amplitude in terms of peak value, peak to peak value, RMS value. I have discussed them in detail, and this is called a time waveform. Time waveform is the graph in which you people will see that on x axis you people have time, on y axis you people have amplitude, okay. So if this is your mean line, so you will see proper distribution of the time waveform. These signals basically tell the behavior of the machine across different intervals of time. What is the vibration amplitude? So here you can see, suppose you have a machine component that consists of shaft, fan lobes and gear system. You can say power transmission system. Okay. So if I will use CSI 2130 for data measurement, that is a multiple channel analyzer. So what will happen? When I will place transducer on the bearing position, I will be getting a time waveform that will be consisting of a signal from shaft, from fan lobes and from gears. Okay. So three types of signals will be there. Obviously bearings will also be present within the system and other components as well. So all of these time waveforms will add up. Okay. Signals of all time waveforms will add up. Maybe it's very smooth, and you people will see when they will add up, then at the end the resultant time waveform will be very complex. You people will be seeing that its behavior is quite difficult to observe. Please check it. Suppose this is the time waveform of the shaft. This is the time waveform of the fan. Previous was the low frequency signal, it is high frequency signal as compared to previous one. Okay. This is another very higher frequency signal. Okay. That means more cycles are present per second. So gears are high frequency faults, bearings are also high frequency faults. Okay. So what will happen at the end? When these faults will add up, or when the vibration signal will add up, then the new time waveform will be like this. So you can see all the three time signals that are present, and resultant time waveform will be like this. So you can see how resultant time waveform is looking, and it is quite complex for us to observe the complex time waveform. So in order to make signals processing easier, Fourier transforms that time domain signal, and using the Fourier transform we can easily represent the time waveform signal into corresponding frequencies of the items. Okay. So what actually amplitude tell us? Amplitude tell us how much where is your fault. Frequency tell us where is the fault. Okay. It will tell us how much, frequency will tell us where, and phase will tell us when that fault is occurring. So this is a short introduction to infrared thermography. It is very useful to diagnose electrical faults and mechanical faults as well, because you people see where there will be a fault, then that joint will have a temperature very higher than the usual temperature. So basically we will check the temperature, and where temperature is higher, that means there is some critical fault at that point. And finally, if we can replace that joint or it will need maintenance, then we decide depending upon the condition. For example, then we can go for the vibration analysis and we can check where is the fault located. So thermography is also very useful technique. Here you can see this is your electrical transmission system. Okay. And you cannot inspect all of the joints at a time. So for that purpose we need to find there was a fault that was found within the breaker. So we will get the help of thermography. So when we will put thermography camera, it will capture image, and based on the convection and radiation heat transfer already you people have studied, it will generate a thermogram. This thermogram will have a temperature scale that will vary from minimum to the maximum scale. Okay. So we can check temperature of each point of the system across the scale. For example, we can see that this zone, almost you can say this 30 degree is temperature of most of the system components, okay, but this component of the system is showing this zone temperature, that is crossing 60 degrees. So that means this component is going 60 degree C and this temperature is higher than the usual temperature. So there is fault at this joint. So we need to inspect that point. So it is very helpful for electrical engineers as well. Thermography is also a very useful technique that is used by electrical engineers as well. So this was your hot connection. Now see its mechanical application. For example, if you are in industry and you want to inspect the machine in short span of time, if you will go for mechanical vibration, then you will collect the vibration data. So what will happen? You will have to collect the data and then you have to perform the signal processing, and at the end you will go for a decision if the vibration levels are high or low. But sometimes vibration levels are not too much high and your vibration collected data is not very helpful. So this doesn't mean that there is no fault within the machine. So thermography will help us that if there is any fault that is initiated, then we can also identify that fault using thermography. So you will see here we have performed thermography of this end of machine and we have found at this end of the, that is basically a non-drive end, and you can see this non-drive end a usual very higher temperature. For example, it is approaching 80 degrees C and it is very higher than the usual temperature, that is about 45 degrees C. Okay. So this means this part of the machine have some kind of fault. So here we people know that normally we people have non-drive end bearing. Okay. So we need to inspect that bearing. So this is how thermography is very helpful by mechanical engineers in order to identify faults. So this was a pump bearing and that was in need of maintenance. So in report we can provide recommendations to check the bearing life, remaining useful life, and if it is coming within the shutdown time then it is okay, but if it is exceeding then we need to go for proper decision. This is your kiln that is normally available in the cement industry, and we need to understand the temperature distribution across the different surfaces of the kiln, because we people know that this kiln is normally maintained at more than 800 degrees centigrade for the proper mixing of the material in order to make the strengthened cement. And you can see this zone of the kiln have low temperature and this zone has very high temperature. So actually a brick wall is maintained inside the inner lining of the kiln. So this is indicating that this surface temperature is going too much high and it can generate cracks and there may be a surface failure because of the development of cracks. So we need to maintain inner lining of the walls within the kiln. So this indicates this surface need maintenance. This is your rotary kiln in cement industry. Okay. This is your another mechanical applications, not only bearing faults, even induction motor faults, gears fault. We can also identify belt drive faults within the machines, because whenever there is a misalignment problem within the belts and pulleys, then you will see that there will be a radial force that will be exerted on the belts and it will generate a heat energy, and this heat energy will be spread across the belt surface and pulleys, and their temperature will be very higher than the usual temperature. So you can see here temperature of the belt is going 183.4 degrees C, and this is indicating that it is more than the usual temperature, because we have a proper available ISO standards and we can measure temperature and we can make a proper decision either this component need a maintenance or not. Thermography can tell us there is a fault, okay, But if we want to identify what type of fault it is, we need to go for vibration analysis. For example, we want to identify there is a misalignment fault within the pulleys, or there is a rubbing within the belt, or belt is cracked, or maybe other faults, or it is too much in tension. So, these kind of faults can be only identified by vibration analysis. Okay. This is general analysis thermography that can help you to understand if there is a existence of the fault. Okay. So, previously I have explained to you people how we can identify fault within anti-friction bearings. Here you can see this is your inner cage, okay, and this is your shaft, and these are your ball bearings, and this is your outer cage. You can see this ball have a proper red color fault, that may be a kind of crack or rubbed material or broken ball. So, when it will spin and revolve around inner and outer cage, so what will happen? It will generate a vibration or force impact within the time waveform if there is fault within the ball. Similarly, if there is fault in the inner cage, then whenever this inner cage will move, it will collide with the balls and it will also create an impact, but of different frequency than the ball spinning. Okay. And similarly, if there is a fault in the outer cage, then it will also be generating a proper impact within the time waveform, but these impacts will be of particular frequency, and we can identify faults either it is in inner cage or outer cage or cage frequency or ball spinning frequency. So, we need to analyze the spectrum analysis spectrum signal or time waveform signal to reach the proper decision that if there is a fault within bearing, then which component of the bearing is affected. So, this is how frequency analysis is very helpful. Yes, I hope this diagram will be very helpful for you people. When you will place your sensor here, okay, this will be your horizontal direction. For example, you can see this man is keeping sensor here. This is horizontal direction in which he is collecting data. If he will place sensor position here, it will be vertical position. Horizontal and vertical positions are combined, known as radial directions. Okay. And this is the axial direction. If I will put sensor here along the direction of shaft, this will be your axial direction. Okay. The perfect direction or perfect position for measurement of the signal is bearing position, because we people know this end consists of bearing, and if there is fault within the machine, then it will be forcefully impacting the bearing. So, that is why we prefer to measure the vibration on the bearing position, okay, on the outer cage that is enclosed within the proper metal box. However, we can also measure vibration at any point of the machine, but this part should be very safe and it should not rotate, otherwise your sensor will try to rotate and it can be very dangerous for you people, even for analyzer as well. Okay. The most impact of the fault frequency is at the bearing position. So, bearing position is always preferred over other positions. However, for structural analysis, we can place the transducers on the base as well. So, you can see this is your axial direction and this is your radial direction, that you can say this is your vertical position and this will be your horizontal direction. Okay. You can see this is your inner race, this is your outer race, this is your ball, and this is your cage that is actually keeping balls at the position. Okay. So, what will happen when the bearing will be adjusted on the shaft and it will rotate, then the movement of the outer cage will be different, movement of the balls will be different, and movement of inner cage will be different. Okay, so what will happen? All of these components will generate a particle time waveform. Okay, and thus they appear with the particle frequency. Frequency of outer cage is called ball pass frequency, outer cage. Similarly, we have inner cage frequency, ball pass frequency, inner race. Similarly, we have ball spin frequency, and similarly we have fundamental train frequency, that is for the only inner cage or train. Here you can see this is your green dot, that is indicating some kind of rubbed surface or cracked surface. So whenever balls will pass through this point, it will generate a impact, and this green signal is shown here. Green signal is shown here. Okay. So this is your green surface when ball is passed through, and this is your green time waveform, that is for the outer race. Okay, and this outer race will generate ball pass frequency. Okay, this is the fault on the inner cage, and whenever it will, because you can see when there is a fault on the inner cage, then the inner cage will move, it will rotate. So this is the signal of the inner cage. This fault is static. This is static. This is moving or revolving. Okay, so we can see difference in the time waveform of this. So inner race is moving and it is generating a white time waveform. And you can see there will be an impact at every instant whenever this fault will go through the ball. And for the green signal, you can see that fault is static and time waveform behavior will be like this. And we can measure the fault frequency by measuring the time period. Because this is your time waveform, I will find the time period and I will take inverse of time period, that frequency, fault frequency. Okay. Now see. I hope this animation will be helpful for you people to understand the time waveform behavior of the inner race and outer race. So we have different frequencies: ball pass frequency, outer race, ball pass frequency, inner race, followed by the ball spin frequency. There will be a fundamental train frequency, and all of these faults are discussed in detail. Okay. So these are your fault frequencies that are found within bearing, and this is one of the practical signal that is obtained from the machine. And you can see that the frequency that is appearing in with harmonics, that is actually bar pass frequency inner race. The software package is very useful to identify fault when you will draw its spectrum from time waveform, and you will provide the bearing information and all the information of components, and it will automatically generate the fault frequencies, and then he will try to find out the fault frequencies within the given spectrum. And here you can see he is saying that this G point that is appearing again and again within spectrum is ball pass frequency in the race. So we can say that there is a fault within the bearing, and fault is located on the inner race. And you can also see RMS amplitude is going very high, that is about 3.24. So this is how we can go for proper decision. So ball pass frequency normally appears at 7.88 orders, which is first mode of failure or first stage of failure. I have already explained the modes of failure in previous slide. You can see that first mode was very clear. Second mode, you can see ball pass frequency in the race that is coming with higher harmonics, and if it is third stage of bearing, then you can see appearing of a side bands. Fundamental defect frequency now appears, and this is your fourth stage of failure, where you will see spectrum will become a mass of noise, and there will be no proper indication, and spectrum will try to fly from the mean position, and this is indicating this is the last stage of bearing failure. Most of the bearings under stage 3 are considered to be under failure, and we need to replace them. This is your failure mode. This is the extraordinary failure mode. So, you can see here there is a fault on the inner cage. So, inner cage have a defect and it is moving, okay, because inner cage always move along the shaft, outer cage is fixed. Okay. So, when its time waveform was gone for the spectrum analysis, here you can observe that ball pass frequency in the race appeared with several harmonics. You can see these red scales that are actually indicating the fault frequency peak, that is from ball pass frequency in the race. And when that bearing was opened and it was found that this surface of bearing was defected on the inner cage. So, this is how vibration analysis is helpful to identify the place of fault as well. Where is the fault located? This is another problem where fault was found on the ball pass frequency outer race, for example, on the interior side of the outer race. Okay. And when the spectrum was drawn, again ball pass frequency outer race spectrum's peaks appear with several harmonics. This was indicating that fault is in outer race. This is another fault, and this is fault on the, you can see this is fault on the ball. Ball is either cracked or rubbed, and when it is moving, and you can see it is generating impact across the time waveform, and when its spectrum is drawn, you can see these harmonics are actually ball spin frequency, data coming from ball spin frequency, and when it was opened, you can see these two dots. This is another dot. So, these are basically rubbed position of the balls that was generating impact within the time waveform, and hence that fault appeared in the spectrum. So, this is how we can decide. So, you can see spectrum behavior of all of the bearing faults, how spectrum is appearing for the bearing faults. Okay. Here you can see fault is in fundamental train frequency, and fundamental train frequency is the frequency that is only subsynchronous. Okay. It may not detect then when with the conventional vibration data fundamental train frequency defects at 0.4 orders shown in peak. So, whenever defect is appearing below 1x, okay, it will be subsynchronous fault, and you can see that machine is running at 1094 rpm, and these spectrum peaks that are scaled down, you can see they belong to a fundamental train frequency. So, it was found that the fundamental train of the bearing was under defect. Okay. This is the time waveform behavior of the bearing, and you can see RMS value is going, sorry, crest factor value is going about 2.38, that is very much higher than the usual value. Okay. This is the another case study of the bearing, and this is the time waveform, and finally when it was fault was easily diagnosed using the vibration analysis. This is the plain bearing defect. Whenever there is excessive clearance or hydraulic instability, then shaft will whirl. So oil will be generated, and it will generate a excitation force that will generate a time waveform impact, and finally it will have a proper spectrum behavior. Okay. So this is all about excessive clearance, and whenever there is excessive clearance within the plane bearing, so spectrum will be showing this kind of spectrum behavior. As the clearance increase, then the harmonics of one time of fundamental frequency will increase and can go up to 10 to 15x. What does this mean? If turning RPM are 100, for example, if machine is moving with 100 RPM, then 100 divided by 60 will be your turning frequency. It is 1.6 hertz. Okay, then he is saying that one peak will generate at 1.6 hertz, other peak will generate at 3.3 hertz, and similarly goes on. It will go up to 15 times. If this kind of behavior appears in spectrum, then it will show a plane bearing fault. Okay, this is oil well fault. You can see that appear at 0.4 orders of the turning speed. Okay, so this is how you can place transducer on the outer casing in vertical direction or here horizontal direction. So this will be very helpful for you to identify fault, or in the axial direction. Then we will generate our time waveform and spectrum for all the directions. Keep in your mind, whenever we go to industry, then nowadays we have a triaxial transducers. In old ages, transducer was only unidirectional. So that's why we need to place transducer one by one in all directions. For example, in vertical direction, in horizontal direction, and axial direction. Okay, while measuring fault on the bearing place. Okay, because all faults of the machines are more prominent at bearing place. So bearing outer coverage, you can say where bearing is spotted, this point is very helpful for the signal measurement. So if you are using uniaxial sensor, you need to measure data in vertical, horizontal, and axial direction one by one. But nowadays, beauty is that triaxial transducers are also available. Okay, so we do not need to measure vibration in all directions because it is automatically triaxial. We just need to place our sensor or transducer at one place, and it will be measuring vibration in horizontal direction, vertical direction, and axial direction as well. Okay, so automatically at that point it will be measuring vibration in all three directions. So this will save time, and in this way we can measure time waveform signal in all the three directions. But these triaxial transducers are very expensive, and they also need advanced analyzers as well. For example, triaxial accelerometer. So these are your belt defects. I have already explained in previous slide. Plain belt or timing belt will have a proper frequency, and how we can find the frequency. This is your belt frequency formula, and we need to find these variables physically, and when we will put in the main formula, then we can find the belt frequency, and within spectrum we need to identify that frequency. If it is present, that means there is a fault within the belt, and it may be because of the pulleys misalignment, that may be angular failure or the overloading, or some other cases as well. Okay. So for timing belt there is also a proper formula. I have explained them in detail. You can say this is your angular misalignment, where shaft is at angle from the one of the shaft is misalignment angularly. So that's why this will generate impact, and finally when we will measure vibration, it will show a proper behavior of the ball pass, it will show a proper behavior of a belt frequency. Okay, and when one pulley is forward and other is backward, so because of the offset misalignment, it will also generate a proper signal behavior. So you can see sometimes belts are cracked and rubbed, and sometimes even sheaves and pulleys are also broken, so they generate a proper impact within the time waveform, and this is how we can identify machine faults. Also look here, internal surface. So these are all different cases of the belt faults. And belt, you can see here belt frequency, this is your belt frequency, this is your belt frequency. 1x belt frequency is showing with harmonics, dominant 2x belt frequency. You can see this harmonics is 2x, this is 1x, and 2x is more prominent than 1x. Okay, the frequency highlighted by the primary cursor is showing that 1 tx of the motor 1 order. Okay, so this is indicating the second peak is 2x belt frequency, suggested that there is a damage to the belt. Okay, so there is a catalog developed by vibration analyst, and we can get help that which belt fault will have which time spectrum behavior. Okay, for example, if there is a fault within belt, then you will see 2x will be more prominent than 1x. Okay, and if belt frequency appears and 2x is more higher than 1x, then in that case you can say that fault is within the belt. Okay, you can see rubbed belt. So the data was collected when machine was in operation, machine was under operation. We do not need to stop the machine. This is the beauty of the condition monitoring, that we can go for online condition monitoring. Okay, and then we can go for data analysis, and finally when we will reach at a proper decision that where is the fault located, then we can turn off our machine and go for the maintenance. It can also move to a scheduled maintenance as well. These are the types of gears fault. Gears are of different types like spur gears, helical gears, bevel gears. I have explained them all in detail. So gear mesh frequency, it is not a gear mesh frequency is always present in the spectrum. Keep in your mind, if gear mesh frequency is present, it doesn't mean that spectrum is showing that fault is within the gears. Okay, gear mesh frequency is a forcing frequency and it will always generate, but sidebands across the gear mesh frequency and pinion and gear frequencies actually decide where is the fault, and either fault is there or not. For example, sometimes when the vibration amplitude of the sidebands is higher than that of the ISO standards, then this identify that fault is within the gears. Now if we further want to find where is the fault located on which gear and which type of fault it is, then we further need to identify the spectrum, which fault frequency is appearing and which sidebands are appearing more and which pinion or gear frequency is more, and even spur gears, if it is broken or cracked or rubbed or backlash or eccentricity problem, then it will be showing a proper spectrum behavior with the higher harmonics of the gear mesh frequency. So this is how we can identify gear faults. The gear mesh frequency should always be present in the spectral data regardless of the gear condition. What is important is the amplitude, as this may vary depending upon gear condition or loading of the gear. Okay, you can see here two mating gears will generate a frequency. Gear mesh frequency will show in the spectral data, and you can see this is your gear mesh frequency. So this is basically a forcing frequency that always appear in spectrum. What are sidebands? Sidebands are the most common indication that a gear is defected. Keep in your mind, sidebands are the most common indication that gear is defected. Sidebands are equally spaced frequencies in the spectral data that materialize either side of the main gear mesh frequency peak. The sideband frequency spacing is equal to either of the turning speed of the input gear or the turning speed of the output gear. Okay, sideband appear with the turning speed of input shaft or output shaft, and whichever sideband is present, it will identify which fault is there. Okay, even from sidebands we can identify fault. If not from sidebands, then we should go for SP and SG, pinion or gear frequencies. This will also be helpful. Sidebands show in data when either the gear is worn, loose or eccentric. The speed of the shaft with the bad gear on it will produce the most dominant sidebands in the spectra. Here you can see this teeth is broken and it is generating a particular meshing behavior, and when it was observed time waveform, then you can see this is your gear mesh frequency that will always appear, but sidebands are also appearing. For example, this is your sideband peak, this is again your sideband peak, this is your sideband peak, this is also your sideband peak, and this sideband peak was appearing. For example, see here, the sidebands are equally spaced at intervals of 310 cpm. 310 cpm. Check the RPM of machine. RPM of machine are 310 cpm or 310 hertz. So what does this mean? So 310 cpm, when you will convert it into hertz, it will be 5.17 hertz. You can see that turning speed frequency is 5.17. Okay, and sidebands are also appearing at 5.17 hertz. So that means that input shaft gear has a fault. The sidebands are equally spaced at intervals of this. This is indicating the gear that rotates at 310 rpm is the one that is worn or damaged. Okay, so from the sidebands we identify which gear is defected. Here sidebands were appearing at 310 rpm. Because how we can find the frequency of the sidebands? For example, if this is your gear mesh frequency, that is about, say it is, suppose for example, if it is 18,000 cpm, suppose this sideband is appearing at 1780 cpm. Okay, then how you can find the sideband frequency? 18,000 minus 1780. Okay, and then you will convert it into hertz. This will be the frequency of sideband. Then you will check which turning shaft have that frequency, either input or output gear shaft, and whichever it will be matching, it will indicate the fault. This is the time waveform representation. Okay, as the defective teeth come into mesh, the noise generate increase, showing the increase in amplitude in the vibration data. So you can also see a crust factor is very important statistical tool to analyze gear faults. Even Curtis value is also very important, and you can see here peak value is small, but crust factor value is very large. That is very important for transient signal analysis or unsteady signal analysis. So crust factor is going very high. This is indicating fault of the gears. Keep in your mind, whenever you are in industry, please do not ignore the G's value as well. G's value is the most important term that is used for high frequency faults. It is basically a unit of acceleration. Okay, and it is used for the bearing faults as well, high frequency faults that are normally with the bearing faults or gear faults. Okay, and these faults are normally judged with Curtis value or crust factor value as well. Sometimes we also need demodulation of the signal, and enveloping techniques is also very helpful to identify fault frequency within the time waveform domain. See here, the input shaft frequency have 1000 rpm. Number of teeth of input and output gear are available. So you can find gear mesh frequency. What will be gear mesh frequency? For example, we will multiply this rpm with this teeth, 1000 multiply by 50 and divide this by 60 to convert into hertz. It will be 833.33 hertz. So you will see gear mesh frequency is 833.33 hertz, and it will be same on both gears. Keep in your mind, gear mesh frequency doesn't mean it is only for one pair of gear. Okay, for example, if we have multiple pairs or multiple stage of gears, okay, then each stage of gear has its own gear mesh frequency, but each pair will have same frequency. For example, if I have a shaft Okay. For example, here we have gears. This is your 3-stage gearbox, 3-stage. Okay, this is your first stage, this is your second, this is your third. Okay, gear mesh frequency for this stage will be 1 gear mesh frequency. Okay, this will have another gear mesh frequency, that will be gear mesh frequency 2. This will have another gear mesh frequency, that will be gear mesh frequency 3. Okay, these gear mesh frequencies will be same for both gears of the pair. For example, either for this gear or this gear, for the same pair gear mesh frequency will be same, it will be gear mesh frequency 1, but for different pairs gear mesh frequency will be different. For this pair gear mesh frequency may be for example, depending upon number of teeth and RPM, it may be for example 250 hertz, it may be 360 hertz, or it may be 550 hertz. Okay, but for the same pair gear mesh frequency will be same. So gear mesh frequency is your input speed into the driver gear. So here you can see gear mesh frequency is 50,000 CPM. When you will divide it by 60, it will be 833.33 hertz. Or if you want to find the order, then what does this mean? For example, if shaft is rotating at 1000 RPM, then it means 50 orders are there with gear mesh frequency. Gear mesh frequency will appear at 50th order of the revolution. For what does this mean? It means when gear will revolve 50 times, then its gear mesh frequency will appear. Okay, this means 50 orders. The gear mesh frequency is the same for both gears as they mesh with each other. So gears that are meshing with each other will have same gear mesh frequency. And output speed is 500 CPM. Okay, I can also prove my answer. For example, if output RPM are 500, and what are the number of teeth of output gear? They are 100 teeth. Okay, so 500 multiplied by 100 divided by 60, because RPM are in minute. So it will be frequency in hertz. It is 833.33 hertz again. So that is same for both gears that are meshing with each other. So gear mesh frequency will always be a multiple of turning speed. For example, it may appear at the multiple orders of the turning speed. For example, here you can see it is appearing at 50th order of the turning frequency. So this is indicating if this is the first order of the turning frequency, then gear mesh frequency is appearing at 50th order, and side bands will also appear. Okay, they belong to either input shaft or output shaft, or input gear or output gear. Okay, so which gear is reflected, side bands will appear with that gear frequency. See this case study that is collected on a fortnightly basis as a part of a routine data collection. You can see this is your spectrum analysis in orders. Why we convert frequency data in orders? We can also convert it into hertz, because sometimes high frequency faults, because gears are high frequency faults, and it may appear near 20 kilohertz or even 50 kilohertz or sometimes 10 kilohertz. Okay, so instead of analyzing data for such a huge frequency, we can convert it into orders by dividing each with the turning frequency. So we can convert it into the frequency orders. Here you can see RPM are with turning frequency is 19.58. Okay, and this gear mesh frequency and side bands are appearing with EE. This is basically a gear mesh frequency side band. So side bands, as the motor is mounted directly into the gearbox, the first helical gear is mounted on the end of the motor shaft. Look here, this is your motor, this is your roller, this is your gearbox. Motor is directly mounted on the input gear. So, what is happening? The spectra data show below is taken from the motor in the axial direction. As the motor is mounted directly into the gearbox, the first helical gear is mounted on the end of the motor shaft. Okay. The gear mesh frequency is highlighted by the primary cursor at 49 Hz. So, this is your gear mesh frequency that is appearing at 49 Hz or 49 orders, sorry. Gear mesh frequency is at 49 orders. The fault frequency data dotted line indicates the sideband data showing gear wear on the first gear in the gear train. Okay. So, basically the sidebands are appearing with the first gear RPM. So, that means fault is with the first gear. Okay. This is the time waveform of that machine that is showing a distinct pattern commonly associated with the gears. The amplitude increases in noise as the damaged teeth come into the mesh. Okay. You can see cross factor value is very high, 4, and G's value is also going very high, for example above 2. So, this is indicating the fault is within gearbox, and further spectrum analysis is indicating where is the fault located within the gearbox. This is the data that is collected on the inboard axial direction. Inboard axial direction. A new gearbox was fitted and new data was taken showing the difference between the good and the bad gear. This is the spectrum of the new gear. One of the gear was replaced that was worn out, and gear was replaced with the new one. So, now your gearbox is now ideal, and you can see gear mesh frequencies are down. You can see only 0.1 RMS value is there and no sidebands are there, or only small amplitude sidebands are there, while in previous cases you can see these sidebands were very high and even they were approaching the gear mesh frequency RMS value or millimeter per second value. Okay. So, this is how we can identify the difference between ideal spectrum and defected spectrum. So, this is your new gearbox and ideal spectrum. So, keep in your mind pinion and gear frequencies always appear, but until and unless sidebands are not there, we cannot say that there is a fault in the gearbox. Okay. So, gear mesh frequency will always appear, gear pinion frequency will always appear. Okay. And pinion frequency or input frequency, input shaft frequency and output shaft frequency, they will appear always. Sometimes gear measure frequency also resonate. Okay. But sidebands will indicate, amplitude of sidebands will indicate how severe is the fault, and then further analysis will indicate where is the fault. So, for pumps, fans, compressors, again same procedure. You have to multiply number of blades or number of fan lobes with the RPM or turning speed and divide it by 60. This will give you a frequency in hertz, and it will appear with several harmonics and sidebands of the turning speed. So, this will indicate the fault within them. Similarly, we can also find the flow turbulence defects. Okay. If there is a flow turbulence, you will see a flow turbulence often occurs in blowers due to the variations in the pressure or velocity of the air in ducts. Random low frequency vibration will be generated possibly in these CPMs range. Okay. So, these are low frequency faults. Turbulence is a low frequency fault that will be generated between 50 to 2000 CPM. So, this will be the range of the appearance of the turbulence spectrum. If this is appearing, it will be appearing in between 50 to 2000 CPM, and it will be indicating fault, that turbulence is there within the blower or other systems. Similarly, cavitation is also another phenomena. Cavitation will generate high frequency broadband energy. So, you can see that this is the low frequency zone, this is the high frequency zone. Okay. And it is starting from here and it is ending here. So, it is quite broadband. So, that is why it generates a very high frequency broadband energy superimposed with ball pass frequency harmonics. Harmonics are with ball pass frequency, and ball pass frequency will also appear in cavitation. Within cavitation, ball pass frequency will appear, its harmonic may appear, and high frequency spectrum will generate a broadband energy. Shape normally indicate suction pressure, erosion of the impeller vanes and pumps casings may occur, sounds like gravel passing through a pump. So, this is the output sound that a inspectionist can hear. So, another phenomena is surging phenomena. Surge can occur if the pressure developed by the compressor is not equal to or greater than the downstream pressure. So, these are two conditions. If they will not match, then what will happen? System will surge. Random low frequency vibration will be generated, possibly 30 to 45% of the compressor speed. Okay. So, for example, it will appear at 0.4 to 0.45 times of turning frequency. Spectrum will appear in case of surging, and this is resonance phenomena, an excitation of a natural frequency by a periodic forcing function. So, this is a process in which natural frequency is excited by the external force or periodic force. Very important thing. If vibration is a fire, then resonance is a fuel. If vibration is a fire, then resonance is a fuel. So, what does this mean? If you want to avoid vibration, or if you want to minimize vibration, vibration cannot be avoided. If you want to say that there should be no vibration from a machine, this cannot happen, but you can minimize vibration. It can be minimized by several other methods as well, I have explained earlier, but root cause analysis is very important, and all the techniques we are studying are root cause analysis techniques. Okay. You can also avoid vibration using the isolators, or by design of shock absorbers, or providing the stiffness and damping elements, or by other methods as well, by changing the excitation frequency. But resonance is a fuel. You need to avoid the resonance as well. And if you will not diagnose the pin fault or root cause fault, if you will not diagnose it, if you will not work on it, this means your system vibration will again generate after some time, and it will go up to a higher RPM and even higher amplitude with resonance. So, this is the phenomena of resonance. The spectrum is showing one time of turning speed of a motor with amplitude reaching 19 millimeter per second. So, this was the case study that belongs to a motor, and you can see one time of turning speed of motor was appearing, and input amplitude was very high. It was 19 millimeter per second, very higher amplitude was appearing here. Okay. So, you can say very often this type of data can be mistaken for an imbalance, as this effect can also produce a high 1Ts. So, one can say that there is a fault in the imbalance. Okay. So, sometimes people can imagine that there is a imbalance fault. So, because of the imbalance fault, turning frequency is appearing. So, in order to avoid that, for example, proper balancing was performed, and again that fault was appearing. In order to help this issue, we need to check the amplitude of the one time of turning frequency 90 degrees to this point. For example, in horizontal and vertical direction, we will check vibration in both directions. This can easily be done by using the multi-point plot in the software. Okay. This was the multi-point plot in the software. This multiple point, you can see the spectrum data. X-axis is the frequency, y-axis is the amplitude RMS value. Okay. The multi-point plot allows the analyst to display several measurement points and same plot. It is very clear that the amplitude of the 1Ts peak are excessive in the horizontal direction when compared with the vertical. What does this mean? This is a characteristic of a resonant condition. Okay. For example, if horizontal amplitude was less than vertical amplitude, you can say it was a imbalance fault. Okay. But according to resonance, horizontal amplitude will always be higher than the vertical amplitude. So, this indicates that fault is because of the resonant condition. So, in order to avoid that resonance, because now we have identified the fault is in the phenomena of the resonance, because machine is properly balanced, but still the turning speed frequency is appearing with high amplitude up to 21 millimeter per second, and horizontal amplitude is higher than the vertical. This is the phenomena of resonance. Okay. So, what happened when compressor was put back into the service? It was noted that it has excessive vibration coming from the unit. The unit was left to run. Okay. This was several months until the vibration became too excessive. Recently, the motor had been replaced due to the bearing defect. However, the new motor was smaller and lighter, but they delivered the same power as the previous motor. So, actually, what happened that there was a motor that was previously installed, and there was the error on the one of the drive end of the motor. So, motor was replaced with the another motor, but its torque was same like the previous motor. So, what had happened when they had replaced the motor, then that fault was appearing. For example, higher turning frequency was appearing with 19 millimeter per second, and they were very worried. For example, they have replaced the motor with the same torque level, but still the problem is there. Data was taken across the unit. The plot above is taken from the motor showing higher peak, and it is exceeding 40 millimeter per second now after some time. So, this was very dangerous condition. This data is very high in amplitude. Data was then displayed in a multi-plot format to show how the amplitude was across the radial planes. So, this is how you can check. This is the horizontal data, this is the vertical position data. Due to the vastly different amplitudes of the first turning frequency, the defect on the motor was resonance. So, we have identified that fault is because of the resonance, not because of the imbalance. Okay. So, what were recommendations? It was determined that the change in the motor size may be cause of the resonance, because they have previously changed the motor because one of the bearing was damaged. So, that motor was gone for the maintenance, and they have replaced the another motor that have the same torque, but resonance phenomena appears. A visual inspection of the framework was revealed that one of the support beams had cracked along the weld, this altering the stiffness of the structure. The support was welded and strengthened. More data was acquired to determine if any effect of resonance had occurred. So, you can see when new motor was installed on the structure or support beam, that new motor was showing a resonance phenomena, and when the inspection of the support was performed, it was found that one of the welded point of that support was broken out, and it had a crack that was developed out, and because of the fatigue phenomena, that crack propagate, and even it became to make the structure less stiffener. Okay. So, because of the crack propagation, stiffness of the structure was decreasing day by day, and its amplitude was increasing day by day. So, this was a phenomena of the resonance. That's why amplitude was increasing. So, I have told you people why resonance appears. And when that fault was removed, that point was again re-welded, okay, and stiffness was restored. Then the spectra shows before. This was the before graph, this is your after graph. You can see very small amount of values of the turning speed. So, this means that fault was because of the resonance, because a crack was generated in the structure, and it was making the structure less stiffening, and hence the resonance point appears. By stiffening the structure in the natural frequency had increased, moving it away from the first turning speed. So, we people know omega n equals square root of k over m. Okay. And when we will increase k, omega n will increase. That means resonant frequency will move away from the turning speed. If turning speed was 100 rpm, okay, but now the natural frequency of the structure is moved up to 550 rpm, suppose. This means now your turning speed is away from the structure natural frequency. So, The basic purpose of teaching mechanical vibration in detail was to let you people know the phenomena of resonance and how we can avoid and how we can properly design the different machine structures. These are different electrical defects not part of your course. Okay, twice line frequency appears, and some of the electrical faults because of the when there will be the loosening within the motor winding, and or some kind the eccentricity of the rotor is disturbed, so it can generate lot of defects. Common faults types that can appear twice line frequency within the spectrum. So twice line frequency have a proper frequency formula, and we can find the twice line frequency of all motors. Okay, and it will appear in the spectrum if your motor has dynamic eccentricity, static eccentricity, loose iron, open or short windings, insulation is broken down, or loose connections. In all of these cases, twice line frequency will originate with higher amplitude and sidebands. Okay, so this was our lecture about vibration analysis in detail. So I was talking about anti-friction bearings. Let me tell you people that anti-friction bearings are journal bearings. They are offered by many companies. SKF is one of the SKF and NTN both are the well renowned manufacturers of the bearings. They make bearing of different shaft sizes. For example, if you will go to website of SKF and you can find the corresponding frequencies of the bearing number, providing the bearing number. Okay, for example, if you people are using SKF bearing, then they have a proper catalog that is provided for each bearing model. Okay, when you will provide the bearing model, they will give you a proper information including all the frequencies, how much load it can be bear, and how much its useful life will be, and how much torque it can bear. Not only this, the perfect grease number for this kind of bearing, and all other parameters as well. Okay, so let me show you one example. For example, sometime you people have to select the bearing, and if you have selected the bearing and you want to find the corresponding natural frequencies of the outer race, inner race, ball frequencies or cage frequencies, then don't worry about that. One way is to use the analytical formula that I have shown you in previous slides. Just put the value of the number of balls, what is the diameter of ball, what is the pit dia of the bearing, and what is the similarly one contact angle is also required. So these are analytical formulas that can provide you with the corresponding frequencies of the bearing. But if similar is the case for gearbox as well. Okay, but if you do not know the number of balls, if because bearing is always enclosed, okay, if it is enclosed within some kind of sport, then you should know about the bearing model. What is the bearing model that is installed and what is its company? For example, if I am using SKF bearing, look example, and I want to find the corresponding frequencies, then I will first of all type SKF bearing calculator tool, and it will give me a website of SKF. Okay, and then I will decide what kind of bearing I have, either it is rolling bearing or a plain bearing. For example, if I am using rolling bearing, then he is asking that bearing you want to find for the properties for the individual bearing or drive and non-drive end bearing, two bearings on the shaft. I will work for the single bearing. Okay, I just want to show you a sample. So he is saying select bearing type. Okay, so here all the types are given: angular contact ball bearing, deep groove ball bearing, and cylindrical rollers, needle type, cylindrical roller type, double cage as well. For example, if I am using ball bearing, it is deep groove ball bearing, for example. Okay, and he is saying you to tell these properties. Okay, but if you do not know these properties, he is saying you to select the designation or model number of the bearing. look here, it is designation. These are the coefficients, load coefficients, and this small d is the dia of the ball, capital D is the dia of the bearing, and B is representing thickness of bearing. Okay. So, select the model number of the bearing. For example, I am using these ball bearing 16007. Okay, and SKF manufacturer next. Okay. Now he is asking me to select calculations. What thing I want to calculate? I want information about minimum load. Okay, bearing rating life, bearing frequencies. In bearing frequencies, you will find inner race frequency, outer cage frequency, balls frequency, cage frequency. All of the frequency will be there. Okay. Basically, I am working for this parameter. I am showing you people minimum load or bearing rating life or viscosity and fits and tolerance, just for your knowledge. Okay. So, we have to provide the following information. What is the radial and axial load? For example, I am providing the radial load 100, sorry, place it 10. Okay. And I am providing the axial load 5 kilonewton. Okay, and speed is about 2000 rpm, and I have to press calculate. When I will press calculate, he will calculate corresponding properties. For example, he have calculated you should use a lubricant grease LGMT2. Okay, and you have to make normal cleanliness, radial cleanliness is normal. Okay, these are your bearing properties. Bearing number is 16007. Minimum load it can carry is 0.068 kilonewton. Viscosity is 2.32. Okay, that is for lubricant. This is the property of the lubricant. Are you getting my point? When you are going to select your lubricant, you have to look for viscosity. Bearing loads. So, he will give you a equivalent dynamic load and load ratio. These are your bearing rating life. So, bearing rating life for the load I have provided and RPM I have given, it will be about, if you are using SKF bearing, then this is your information about useful life of the bearing. Basically, this was the factor of interest, fault frequencies. These are your required frequencies. You can see if I am using the bearing model of 16007 SKF bearing, then inner race frequency will be 33 hertz, outer race frequency will be, it is not given, rolling element frequency is 14, okay, and about its axis will be 125, and similarly these are other frequencies that are also sometimes required. So, this is how you can calculate the corresponding frequencies, and you can save the information for the bearing. So, this is very important tool. Similarly, NTN bearing selection tool is also available. What kind of manufacturer you people are using? All right. Similarly, for gear mesh frequencies, Movies Institute has provided different calculators. For example, for gearbox, here you can see, here you have to select the number of stages and RPM and Fmax and the number of teeth, and they will provide you with the what will be the gear mesh frequency and sidebands and so on. Okay, he will may provide you a complete spectrum how it will be looking. For example, for bearings, look here, and this is your NTN bearing, and you can see the grease code recommended is LP03. And what are the chemical properties? It is more resistant to centrifugal force induced leakage. Fouling from grease leaks or around the bearing is positively prevented. Water does not emulsify the grease or cause the grease to leak. The grease has a longer lubrication life. Unlike ordinary grease, bearings with solid grease exhibits virtually no steering drag and therefore contributes to the lower bearing torque. Permissible operating temperature range and speed. Temperature at bearing outer ring. Use the bearing in a temperature range of -20 to 80 degrees C and maximum 60 degrees C for continuous operation, and permissible DN value is bore diameter value is this for this grease code. So, you can see the solid grease how it is helpful for case of bearings, and these are your, this is your outer cage and this inside is your inner cage, and this is basically your that is covering the cage that is covering the balls, and these are inside deep groove balls. Okay. Now look here, whenever there is a failure within case of bearing because of contamination within the grease or dynamic loading or because the life of the bearing decrease. So, you can see when we open it how the cage basically appears. This is your cage. So, there may be a fault within the balls or cage. So, depends, sometimes cage may break because of the higher axial force as well. Here you can see the fault on the ball. This ball is rubbed here. If you are looking here, please see it. If it is visible, please see here, this one, this point. So, you can see a proper rub here. Okay. Similarly, look here, this is your inner race, and the inner race consists of several rubs and cracks, and whenever balls will pass through them, then they will create an impact force within the time wave form and corresponding spectrum will generate indicating a fault. So, this is the condition of bearing when we open them. They may have fault in the inner race and outer race, similarly bearings and cage faults as well. This is your cage fault. Okay. And sometimes there is a contamination in the grease as well, it also generate a proper spectrum module. So, this is how you are looking in the race. So, it will generate a very high nature of vibration. Sometimes in case of bearings, people do not install them in a proper way. So, that is why you have seen that within the suggestions of the bearing faults, it was properly written that because of the contamination error and installation errors and manufacturing error, the actual bearing life always decrease and only 10% of the suggested life is only achieved. So, for example, look here, I have also worked for some time in industry and I have seen people installing bearing, and I was shocked that how they are making bearing installation. The actual way of bearing installation as suggested by the manufacturer, for example NTN, please look here one of the video. this was your proper method of bearing installation, how you can increase the reliability of your product. This is proper ways and steps. Sometimes people install bearing and impact force they are providing from hammer. So during installation, even during installation, they go for damaging their system. Inner cage may be defected, or there may be generation of the impact on the balls or the inner outer race. So that's why it is very dangerous for all. This is one of the video that is based on the signals processing, machine fault diagnosis, structural analysis. In this video, I have told different softwares that are used for the vibration analysis. I have explained how we can collect different vibration signals using transducers or accelerometers, and then I have explained using the different softwares how to draw the time waveform and frequency spectrums. I will request you people to watch this video if you properly want to understand how we can perform signal processing and how to draw the time waveform and frequency spectrums for the machine fault diagnosis. For example, in this video you can see the software I am using and drawing time waveform. This is a signal software. I have imported the signal and providing the sampling rate, and then I have plotted its frequency spectrum. This is a frequency spectrum. On axis it is your frequency in hertz, y axis is your amplitude, acceleration amplitude. So this is another signal. You can see clearly the spectrogram indicating the fault frequencies and other peaks. And these peaks help us to identify different machine faults. This is the RMS value of the signal, or root mean square value, and this is the another scaleogram that we normally plot. It provides three-dimensional analysis, for example time waveform, frequency analysis and amplitude. When you will see this video, inshallah this video will be very helpful for you people. This spectrogram, how we can plot it. So please see that video. I hope it will be very helpful for you people if you properly want to understand how we can perform vibration analysis. Now in the end, I want to enclose my lecture with some of the suggestions from my side for you people, because this was our last lecture that are discussed till now, and in addition sometime I will also try to upload the software analysis using NCS, how to perform the multiple degrees of freedom. I will, because we are already doing design a machine elements lab. In this lab I will tell you people how to perform the model analysis using MATLAB and NCS, and I will upload its video here on this channel as well. And please see following suggestions from me, as this is our last class with mechanical vibration. I believe that you people will have to face many bad and hard times in your life. So the main thing is that I'm suggesting you people that never lose hope. Okay, hope is not a good thing, but also a very good thing. After the heavy rain, you will see the sunshine. So always be positive. I am proud that I have got the chance to teach you people. Uh, Although our lectures were very boring because we people have to perform certain mathematical models, analytical models, and to perform the numericals and to understand the theory. And this all course was very heavy, and in this situation of COVID-19, so I know you people will have a lot of troubles, but it's sorry from my side if I have never uh, almost I have tried my best to help you people and to convey with best of my knowledge, but it may be possible with some students that I have not properly guided them. You are all very brave and active. Always keep your spirits up. And I wish that all the very best to all of you. And you people know when there will be your success, it will be my success. When you people will be in a better position in your future life, then it will be my success as well. So it is my suggestion, please work hard and achieve your success. Be a good human and always help other people throughout the country and even throughout the world. So be a good partner, be a good friend, be a good soul, and be honest and responsible person in your life. Okay, so you are a person who can change the world and you have a big responsibilities ahead, and I know you can do it because you people are very brave and active. So all the best from my side to you people. Best of luck for your exams as well. Thank you very much for your hearing patience. Take care. Allah Hafiz.